steps. So nowadays we can say that we have very good weather forecast up to 10 days. But what will happen with the condition of the next 2-3 weeks or 1 month? So although we cannot predict individual weather events beyond roughly 10 or 15 days, on monthly and longer timescales, the climate, and we think the climate as the average of weather events, can be modulated by different components of the system toward a particular climatic state. So I really like this experiment. I think it was Tim Palmer, the one that first introduced it. So we have here a ball that falls and can go to one or the other side. So in absence of any change in the climate component, if we throw a ball, we'll see that it will likely go to both sides. So at the end, we will have balls on the left-hand side or the right-hand side. But we think this experiment will add a fan, so that will represent a change in the climate component. At the end of the experiments, we will have more balls on this side. However, that doesn't mean that the ball can't fall on the other side. So what represents is, what can we say about climate prediction in the next weeks or months? We cannot say how individual events will behave in the future, but we can say, okay, we expect more balls in this side of the experiment because we have a fan that will move the ball in that direction. So that's what we can say in climate prediction, what we are referring to how the climate will be in the future. Oh, what happened? Oh, here we are. So I really like this experiment by Shukla that he did in the 90s, because was one of the first work that illustrated how climate predictability work. So what he did, so he took the SST conditions in 1982, 1983. Maybe you've heard about this year, but it was a very strong Niño event occurring that moment. So he took it in January, February, took the SST in 1982, 1983, December, January, and February. And then what he did is he coupled this SST with different initial conditions. So in one experiment, he used 5 initial conditions of the atmosphere from December 1988. And in another experiment, 5 initial conditions of the atmosphere from December 1982. And then he ran a coupled climate model, the Koala climate model at that moment. And at the end, he computed the precipitation for January, February, and March. And look, we started with a similar or same SSTs, but a different atmosphere. What happened with the seasonal behavior of the precipitation? We see that the difference between both simulations is actually very small. We see that the large-scale patterns, the negative anomalies in the west and the positive anomalies in the central Pacific, are quite similar between both experiments. And if we compare that with the observation, we actually see that the model did a good work at trying to represent the precipitation in this case. But the atmosphere was different. So what happened? Well, what actually happened is that the ocean acted as the fan in the previous experiment, and shift or pose a condition in the atmosphere that led to more negative anomalies in the Western Pacific, positive in the Central Pacific, such those that we see during El Niño conditions. So look that if we know the condition of a component of the climate system, that could be the ocean, could be the land, could be the stratosphere, could also be the sea ice, we could say something about the climate in the next season. Oh. Okay. So when we talk about climate prediction, we make a distinction. So when we talk about weather forecasts, we are thinking in timescale up to 10 to 15 days. And in this case, the forecast that we're making is very sensitive to initial conditions. So it's mainly deterministic. So we usually say, okay, temperature for the next 2 days are XX degrees, although always probabilistic prediction is decidable because we don't know perfectly that weather forecast, although we know that we are very good at predicting weather conditions. For climate predictions, we're thinking in predicting the mean conditions of the next weeks, the next seasons, or longer timescales, and is inherently probabilistic. So we are talking about chances of wetter or a drier season, colder and warmer weeks, for instance. But even though we are not saying a definite value for that week or that season, we know that it's very useful for agriculture, energy, tourism, and health because they are very familiar with the expected climate conditions. And if we are telling them, look, next week's going to be very wet, they can plan the activities and move it to adapt their activities to the expected outcome. So when we're talking about climate prediction, we're thinking in timescales of 2 to 6 weeks. That's the domain of the sub-seasonal prediction. We're thinking of 3 months to 6 to 9 months, and that's the domain of the seasonal prediction. And then for longer timescales, most of them we're thinking interannual prediction and even interdecadal prediction. So I would like to briefly introduce some progress in the last years in climate prediction, in particular in the region of West Africa. So I will introduce some examples for precipitation because I know that during the afternoon you will hear about the prediction of heat waves. So I will not touch the problem of temperature. I will just present some examples of what has been done in terms of seasonal and sub-seasonal prediction of precipitation. So there is a recent work in 2020 that did an objective evaluation of precipitation seasonal forecast during the rainy season, July, August, and September in West Africa, in particular during this region that I'm showing with my mouse. So they took 5 dynamical systems that are very popular for seasonal prediction: the Met Office, the NCEF CFS version 2, the ECMWF, and Meteo France model. And they first compare deterministically what happens with precipitation during July, August, September, comparing the forecast against the observations. These forecasts were initialized in May. So we see that this is the color scale. So we have some regions, especially in the southern part of the domain, in which the correlation is quite good. So the anomalies of the forecast follow the anomalies observed. But then if we move closer to the west and the northwest part of the domain, we see that this performance drops. But then when we compare and we take all the ensembles that we have for those predictions, and we create probabilistic forecast, and we compare with the observations, we have different scores that we can use and different aspects of the model that we can compare. We can see if there is a strong correspondence between the probability that we issue versus the observation. We can also evaluate if the forecast can discriminate situations in which the occurrence of an event is likely versus unlikely. And we use different scores to do that. So here are 2 examples using one that is called the rock score or rock diagram. That is in the upper part. So the idea is that we need to go very up in this square to get a good score. And if we are close to the diagonal, our forecast is not very, very good. And in the lower part of the presentations, we have the reliability diagram. And the idea here is we would like to have a strong correspondence between the observations in the y-axis and the forecast in the x-axis. So a diagonal will be desirable in this case. So we see that even though the forecasts have a good correspondence in terms of deterministic scores, such as the correlation, when we look into probabilistic forecasts, there's still some problems in the system because we don't have a good discrimination of the events, and it's not very reliable. None of these systems have this property. Another aspect of the precipitation that we may be interested is in predicting the onset of the rainy season. We know that in many regions of Africa, not only in Africa, in other regions as well, we have something similar in South America. Maybe we are not interested in knowing how much will rain the next 2 or 3 weeks, but we would like to know the moment in which the rainy season will start. So we plan our activities around that date. So there is an interesting work by Saipieri that shows in this the left-hand side the mean rainfall onset in terms of days since the beginning of this 6-month period. So we have Jan, June, February, July, March, August, etc., to December, May. And the color shows the date of the onset as a departure of this day from January, February, March, etc. So for the West Africa, we are interested mainly in what happens between April, September, May, October, June, and November, because that's very close to the onset of the rainy season. And then in the left-hand side, they look at the error of the forecast in predicting that beginning of the rainy season. So if we think in some domains of Africa show very interesting skill, we are looking at values above 0. That means that we can do the forecast can do a better prediction than using the climatological value of the onset as a predicting tool. So if we think of regions in Eastern Africa or South Africa, we see that we actually have a good skill. But when we look at Western Africa, we see that in this case, many regions have negative values and very few have positive values. So modern seasonal forecasts still struggle to predict the onset of the rainy season. And that may be also a diagnostic of why the seasonal forecasts are still struggling in predicting climate conditions for the rainy season in that region. But well, maybe we cannot say a lot about the conditions on a seasonal timescale, but maybe if we move to the subseasonal timescale, there's something useful and information that we can still extract from the forecast. So in the context of the SWIFT project that occurred in the last years, in collaboration, scientists in collaboration between institutions in Africa and also in Reading University investigated a lot the use of subseasonal forecasts for different applications. And there is a very interesting study by the Andrade showing the performance of subseasonal forecasts in predicting weekly precipitation anomalies in different regions of African continent. I just show results for the West Africa domain. So in this case, we're focused on the next 4 weeks, and we try to say how are the mean rainfall conditions for those weeks. And they evaluated 4 different models. Those models are actually the similar that I showed in the first work, but now for the subseasonal timescale. So they're looking at weekly timescales. And they used similar scores that before, the ROC score. So we're looking values above the diagonal, the larger the better, and the reliability diagonal. So a perfect diagonal is desired. And we can see that For week 1, there is actually some discrimination of the forecast. So when a forecast issue a large probability for an event to occur, in this case, the occurrence or non-occurrence of precipitation, we see that the chance or the probability of having a false alarm is low. But when we move into week 3 and week 4, we see that the quality of this forecast reduces. When we look at the reliability, we see that there is not a good correspondence between the forecast probability that we issue and the observed frequency. So there is still some work that we need to do in terms of improve the quality of subseasonal forecasts to have reliable and forecasts with good discrimination. So, but if we look at these works, we may think, okay, there's nothing we can do. There's still a lot of work, and how can I use this forecast information? So I would try to summarize some work that could be useful in trying to improve models and also think about what are the aspects that we need to improve of the model. So if we have a diagnostic of what's going on with the models, that's a very useful information, because then we can think on either correcting the model, inform these to model developers to see if there is a way to improve the performance of the model. But also we can anticipate that if a forecast issue an outcome, but we know that there are some shortcomings in that model, we can anticipate those shortcomings and communicate them. So there is a very interesting work using a different set of seasonal forecasts, trying to look at what makes them a good forecast for the West African region. So they're looking in precipitation in July, August, and September. And we know that there is a connection between the ENSO conditions and the precipitation anomalies in this region. But we know that when there is a El Niño, there are larger chances of having precipitation above the median in that region. So, and in this work, they also mentioned that the SST variability in the Eastern Mediterranean region is also connected with rainfall variability in this region. So they look at how well do models predict precipitation in July, August, and September for different lead times. So they have a set of models, and they try to predict this precipitation with models initialized in July, June, May, April, March, and they go up to February, so like 6 months before the event to occur. And they looked at, okay, if you are close to the event, your correlation is actually quite good. So it's like about 0.8, 0.6 for some models. So it's significant. And if you move back in time, you can find that some models actually show some correlation with precipitation. So you could have a good deterministic score if you move beyond the date and try to anticipate the rainfall conditions. But they say, okay, there are a lot of models that actually are not doing very well. So what they did is also try to see how well do these models predict SST anomalies in El Niño 3 region, and how well do they predict SST anomalies in the Eastern Mediterranean condition. So they looked at, while they are doing a very good job at predicting El Niño 3, looked at this color bar goes from 0.4 to 1, so most of the correlations are significant and are actually very large. If we take the predictions done in July, we can see that for the Eastern Mediterranean, not all the models are able to predict the conditions there. So maybe if we improve how well do models predict SST conditions in Mediterranean, we know that there is a relationship between SST there and precipitation, and that may lead to a better prediction of precipitation. So improving this link may help to do. If we look at the subseasonal timescales, the work of the Andrade not only showed the score for the subseasonal prediction, but also shows some hint of what models can improve to improve subseasonal forecast in the region. So we have here the regression coefficient between some large-scale climate drivers and June, July, August weekly precipitation. So we see that there is a negative correlation with El Niño and precipitation, we already know that, and positive correlation with the Indian Ocean dipole, and a negative correlation with the two indices that are used to describe the Madden-Julian oscillation, that is a mode of variability for subseasonal timescales. But then they also look at the difference between these regression coefficients and the coefficients that they obtained with one of the models that they used. And we see that for the different weeks, we have very large difference between the regression coefficient for those indices that describe the MJO that are used by the model versus the observed one. So if we can improve the connection between MJO and weekly precipitation, this eventually could lead to an improvement of weekly precipitation. For longer timescales, we also see that the difference between these regression coefficients for the IOD also is quite large. So it will be important for models to improve the link between the IOD and precipitation, also to improve the performance of models for that region. This work is very interesting because not only depict this type of analysis for the West African monsoon region, but also for other regions in the study. So maybe you are not directly based in West African monsoon, but you're interested in other regions. You can also check for this figure in this paper to better understand what's going wrong with the model, so we can improve the predictions. But even though forecasts are not perfect for these timescales, we still have an opportunity to exploit the information that they give us. So there is one approach that's been used by the community in the last years that implies an interaction between scientists, practitioners, stakeholders to see and to explore how can we extract more information from the forecast, how we can depict the forecast information so that can lead to better decisions for the different sectors. So this approach is usually referred to as a co-production approach, and it has proven to be very useful for different applications. We've used this approach in our work with farmers in northwestern Argentina, but there is an interesting paper showing applications for the energy sector. This, I think, is for Kenya. Now, this work has been done by scientists and practitioners in the Kenyan Met Service. And they started with the forecast of the information that was issued by the Met Service at the beginning of the project. Now, the information was depicted this way and have a reference of how to read the forecast for the next months. And through a cycle of interaction between researchers, practitioners, and stakeholders, this way of depicting the forecast has evolved, has changed, and went from the figure shown in the panel A to the figure shown in panel D, that also include information from previous year climatology, current forecast, the uncertainty, and that has led to better decisions in terms of how to manage the power generation from the hydropower plants. And it's very interesting, the article, because has shown that they tested all the way that the information is presented in a 2-year period, and they show that the number of blackouts in that region has reduced, and that's because the power generation in the region has changed after we integrated or we explored better ways of show the forecasts are more useful for the decisions they're making. So I would like to finish by saying that we've seen different skills of the forecast, how are they doing, the seasonal and the subseasonal scales. But when we're talking about using this information by stakeholder, we would like to transmit or to inform some reliability. So we need to have meteorological skill in this forecast. So we need to work towards getting more skill in our forecast and possibly doing a diagnostic of how models perform. It's a good way to explore how to get better skill from the predictions. And for a forecast to be actionable, it also needs to be relevant to the decision and the decision that the user is trying to make. So I showed that with the example of the co-production, how the way that the forecast information changed and how that helped to make better decisions. Something that is also important is that this information on the future climate condition needs to arrive in time. That's the only way that an action can be taken by or led or using forecast information or driven by this forecast information. If this information arrived after, I don't know, the meeting between the user is done and the decision is made, is useless. So it's important that even with the current generation of forecasts, we improve the communication of the existing and the new forecast products. So if it's important if when we have a forecast, see, okay, try to analyze, is this the best way that we have to show the information, other ways to communicate it? It's important to have a good dialogue with stakeholders to see what they're interpreting by the forecast and what are the ways that we can improve. And that can only be done if we have a collaboration between researchers, practitioners, stakeholders, because otherwise we are issuing forecasts, but they are not being used for decisions. And I already uploaded my presentation in the folders, and there you have all the references that you can check. But there is also my email if you want to ask me questions. And that's all.
Thank you very much, Osman. So thank you for your nice talk. Any questions from the audience here in the classroom? Questions? Okay.
Hi, Marisol. Thank you for a nice talk. At some point, you showed the ENSO teleconnections on African precipitations. I mean, do you have any idea what is the mechanism behind?
So usually for the ENSO to influence precipitation, there are two ways of doing that. Depends on the latitude where the region you are looking at. So for tropical or all the locations in the tropical region usually is because the ENSO changed the way the water circulation works. So there is a meridional movement of the water circulation, that affects the regions when you have enhanced precipitation or suppressed precipitation. So that's one mechanism. But the other mechanism is that you have a source of Raspberry waves that can move meridionally and influence remote region. That's why, despite that ENSO, it's a phenomenon that occurs in the Pacific, it can influence other regions in the world because there is a big change not only in the tropical conditions through the water circulation, but also intratropical through Raspberry waves. So this direct mechanism is more predictable. So usually you have a better link in tropical regions and also a better skill because of that. But in the extratropical regions, it's more challenging because you have influence of other phenomena and they are not always in the same location.
Okay. Is there any primal pathway, tropics or subtropics? Raspberry wave?
No, the most important is the tropical mechanism that's direct, and then you have the extratropical one that it's less predictable. So for Africa, I would say that for the tropical region, it's more important the change in the water circulation, but then you also have the influence of the Raspberry. That's the second place.
Okay, thanks.
All right. Other questions? Okay, so we also have questions online, right?
Yes, I also have a question. If
Okay, so let us take one question from the classroom and then we will get back to you.
okay, thank you.
Welcome.
Thank you for your nice presentation. If I have authorization, I have 3 quick question, if possible. Okay. Okay. So I would like to know whether you are able to combine data model and in situ model. But I think it's very good to combine this because I work in my service. So I'm in the Med Service Senegal about seasonal and sub-seasonal forecasts for rain and for heat. The second question is have you able tested your approach during extreme heat during because it is a very challenge in West Africa to try to do the seasonal forecast for heat extreme. And the last one is how do you think different basin can be combined to better using AI? About my first question at the morning, because we are a workshop about climate and AI.
Yes, okay. So if I remember correctly, the first was about combination of models and in situ models. I think you're talking about regional models, regional climate models, if I'm correct. So that I can share with you, there are some works trying to do some downscaling using the seasonal forecast as an input and then using the regional climate models. My experience is that that's a useful approach when you're looking into regions with very complex terrain, that for reasons in which the topography is not very challenging, it's still better to stick to the seasonal climate information that we already have from the large scale models. The second was about heat waves. I will not spoil that because in the afternoon you will hear about that. So wait for the afternoon. I think you have a very interesting talk about a recent paper on how to predict heat waves. Yeah, and actually the talk will be given by one of the authors of that article. It's a very good one. And the last one was about AI. Okay, so I'm not an expert in AI, but what I read about the use of AI for seasonal forecasts is mainly trying to actually correct the model deficiencies using AI. So what I see is there are some work that look at the forecast, the seasonal forecast in the past, and they compare it with the observations, and they use different machine learning models to see if we can correct some model deficiencies and use that correction approach in the future. So the upcoming forecast do not have the same deficiencies that they show in the past. So that's been the main approach of using AI for seasonal prediction.
Thank you. Online, Oredola, Ibrahim, your question? Ibrahim.
It was this. It was this.
Oh.
Go ahead, please. Go ahead. Sorry.
Okay, thank you so much, Marisol, for your presentation. And I'd like also to pose a question on WAF model performance, especially when it comes to topographic features and the elevation. At some point, the performance tend to be reduced. How can you comment on that?
Okay.
Yes, as I said, that it's not a problem. That it's a common problem across models. That's my first point. It's not only seen in seasonal forecast, but well, one approach could be, especially if you try to do applications, use regional climate models that have seasonal forecast as an input, because we know that in this case, if we increase the resolution, we can better see the topography in the domain, and possibly that can lead to a better representation of climate phenomena in complex terrain. But so that's one of the main approach. Other other works also used observations in the past from those regions to do a more statistical downscale instead of a dynamical downscale. So trying to relate what the models saw in the past versus what was observed and extract a relationship of that, and then use that relationship in the future to anticipate the next what will happen in the next season through this relation between the observations and the forecast.
Okay, thank you. Well, we still have questions, but I think we are running out of time. You have her contact. Maybe you can email her directly.
Of
Okay.
course, you're welcome to
Thank
email
you
me.
very much, and let's thank the speaker again.
Thank you, and apologize for my voice. It's like 6 a.m. here, so I'm a bit sleepy yet.
All right, so the talk continues. Then we are going to welcome the next speaker. Is your talk ready? All right, good. So let us welcome Prof. Maria Molina from the University of Maryland, USA. She will present the overview of artificial intelligence for weather and climate predictions, advantages and limitations. You need this one?
Yeah, so that the online can hear. Hello. Hi, everyone. It's been great to be with you this week. So today I'm going to be speaking to you about a couple of topics. The first talk, that's before our break, is going to be a general overview of AI for weather and climate prediction. And we're going to also talk about specific advantages and limitations. After the break, we're going to talk about specific examples and use cases of AI for weather and climate. And I know a few of you have had those types of questions, so I'm excited to address some of those. And so for this talk, I'm going to essentially give a history and general evolution of AI, machine learning, and deep learning. We're going to talk about different types of learning that may be relevant to your specific problems and questions that you have. And we'll also, again, hit these advantages and limitations. So first of all, when we're thinking about what is machine learning, when we're thinking about without machine learning, we have the example on the left-hand side where essentially we are using a computer and we provide very specific instructions in software for whatever we want to do. So these are like our expert systems where we might say, okay, a tropical cyclone is defined as something that has winds maximum sustained 3-minute at 74 miles per hour. I'm sorry, I don't know the not miles version, but so essentially we're going to set very specific heuristics, thresholds, that type of information, which unfortunately breaks down in weather and climate, right? So we know that there are some extreme scenarios or very weak scenarios that still produce very damaging impacts. And so that's an issue when we're dealing with very specific instructions. So the advantage of machine learning and the power of machine learning for weather and climate is that now we can just provide data for our problem and hopefully the models, et cetera, that we train are a lot more robust. And so you'll hear me use a lot of these words interchangeably, but I do want to quickly set the scene. When we're thinking about these different terms, computer science is sort of at the top level hierarchy, the more general term. AI includes not only the models that we'll be talking about today and tomorrow, but it also includes a theory of AI, like what is intelligence. When we get to machine learning, we're talking about any model that can learn from data, and the defined definition from the 1950s is provided here on the screen, which is essentially the ability of a computer to learn from data. So very broad overarching definition. And then deep learning is a very specific example of machine learning where we're only talking about neural networks. And so when we're talking about neural networks, there are a few different flavors of neural networks. The simplest version of a neural network would be something like this illustration on the top left, where we have a number of hidden layers. Here we have 2 hidden layers. Each one of these has 8 nodes. The inputs are like your variables for weather or climate. And then the last neuron is the output, so the prediction in this case, right? And so one of these neurons does this calculation that you have on the screen. And so essentially what's happening is we have this neuron receiving signals from the earlier layer, and that's your X, so whatever your data is. And this is what is learned, the W. So those are your weights. The number of nodes, that's the number of weights. So that's why we have a little I there. And then we also have a bias term that can be added. And all of the multiplications between the input and weights get summed. So that's why you can process a number of different signals. All of this then gets passed through an activation function, which can introduce some nonlinearity should you want it. Cool? It gets a little more complicated in reality, even for one neuron, because now we have to sum this over many samples. So it's not just one example that the artificial neural network is going to use. It's going to have a mini batch. So we're going to give it something like 16, 32, or even up to like 256 samples at a time. And this math is just for one neuron. So this artificial neural network is relatively simple that we have illustrated here, just 2 layers, 8 nodes each, but you can see how that complexity quickly increases when you start envisioning that calculation on each node, right? And then scale that up to a more complex neural network with many layers, many nodes. There's a lot of that math, very repetitive, right? And so, but that actually gives it the power to learn so many nonlinear signals and complexities in our large data sets. And so the way that it learns is that then it updates these weights using different backpropagation rules. So here we have a very simple example. This is probably, I think, one of the earlier ones where we can have a parameter. So this would be your weight or your bias that's going to be updated. And so you have your original one, and then you get your new version of that. The alpha is a learning rate. So this is something called a hyperparameter that you predefine. You'll be seeing these hyperparameters in your notebooks and activities. And so that's how much you allow the parameter, so your weight, to change per iteration. And then we also have the gradient of the loss with respect to the parameter, which is absolutely crucial for supervised learning examples, where essentially we let the neural network make a prediction, and then we calculate an error, and then our goal is to reduce that error by updating the parameter to make the error smaller, right? Awesome. And so what I just explained again was like the simplest flavor of a neural network, of a deep learning model or a neural network. So that was a fully connected neural network. And the history of deep learning is quite rich. In fact, if we go back to the 1950s to where we first had it defined, there were periods of reduced excitement for AI development. So this is the 1970s and 1990s, which is often referred to as AI winters, where there was reduced funding. Some of that came from too much hype and expectation that then was just unmet by developments. We also have this, the 80s was marked by a lot of excitement over those expert systems. So giving computers explicit instructions, and then you can scale up calculations very quickly. But of course, that's not going to be enough to get you towards more generalizability with models. So you can imagine why we had then our second AI winter. We still lack technological advancement or sufficient technology to be able to really scale these up. But just the last couple of decades have seen a continued upward trend. So many of you likely are familiar with things like convolutional neural networks. So that was back in the late 1990s, where we had a landmark paper come out. More recently, there was a paper on attention, which is over here in 2017. So that was the advancement of transformers, or more specifically, the self-attention mechanism, where you can give a neural network a sequence of data, so like a time series, and then it would allow it to look at some parts of that sequence and identify what was most important for its respective task. And so that really helped accelerate processing, et cetera, and scaling of things like large language models, which eventually led us to where we are today. We've got our, let me see if I can reach this. Can someone help me minimize this video? Thank you. Yay, okay, thanks. Yeah, so we've got so much history that I needed to use a full slide. So we've got, of course, the most recent time period that all of you are experiencing, which is this ChatGPT, this adoption of diffusion and other advancements, which have, again, continued to raise excitement for deep learning. And when we're thinking about AI, there's a number of reasons why we are so excited about it, right? So we've had this growth of digital data sets that have enabled the training of large models. This includes labeled data sets. So in Stanford in like the 2000s, there were a number of graduate students that were grouped together and asked to look at a bunch of photos of bicycles and dogs and cats, and they had to label them, right? But that enabled the benchmarking of image classification models. So that was really important work. And more recently with ChatGPT and other such models, we also have unlabeled data where we can just process these sequences and learn from them. But of course, technological updates, things like GPUs, other innovations in terms of algorithms. So we talked about the attention mechanism. Also really critical, something that I think gets downplayed when we think about all of the advances in AI, is the open source nature of software, because that's created this very large user base, large community, people developing tutorials, putting them online, and then you can access them, right? And standardized benchmarks, as well as investment that's been driving this. But I want to emphasize that the open source availability of things like PyTorch, Keras, TensorFlow means that we have very robust software that is constantly being checked by the community. So if I go use Keras and I run into a bug or I'm getting something weird, I go on GitHub and I'm like, hey, go to my issues, what's happening? I can, what's this error? Or I look at other people that's got the same error, right? So that really fosters continued advancement and development. And this open source ecosystem also means that, that deep learning libraries that use Python can leverage other libraries written in Python for scientific computing. So if we think about the workflow for training a convolutional neural network, for example, step one would involve your data preprocessing. You can use libraries like SciPy to look at the statistical distribution of your data, to understand your data and make decisions about the architecture you're going to use. Then you've got your deep learning libraries, but then after you train your machine learning model, you still need to evaluate that model. So what will you use for evaluation? Things like scikit-learn, things like any other customized package out there, even something as simple as pandas, to be able to look at, again, how well that model performed. And we can also use visualization software. So there is some sort of Python library that can carry you through that full workflow from start to finish. So different types of learning. I think we briefly brought this up on day one when we talked about regression and classification, but I wanted to make clear that when we're talking about supervised learning, these are cases where we have some ground truth or some label that we want to answer. So for instance, if we're thinking about the process for labeling or generating a prediction with the machine learning model, we would need, this is just a workflow. This is not how an actual neural network works. Normally your label goes over here. So you would need to have labeled data, your predictors. Can we stop with the chat? So we have our predictors and our predictants, right? And we have those put aside and we're ready to train a model. And then we are able to generate predictions with our machine learning model. So if we think about a linear regression, so really simple, y equals mx plus b, m being the slope, x is your input variable, y is your y-axis, your answer. This would be a supervised learning example, right? So you kind of already know what your y is, and you're trying to fit a slope so that you minimize, let's say, mean squared error for that y. For unsupervised learning, we in this case don't really know the answer beforehand, and we're really just trying to uncover patterns in our data. And so in this case, we don't have a y. So those are your two sort of classic paradigms, but you don't have to be limited if you only have some labels. So let's say grad students went on strike. They said, no, we're done labeling. We only labeled a little bit. All right, so what would you do? Then if you still need to write your dissertation and you only have some labeled data, in this case, you can turn to something like semi-supervised learning, where you have a mix of some labeled data, and you can use that for the task, but then you also use your samples that don't have labels. So you can sort of work in that space where maybe it's just too expensive, human resource wise or computationally, et cetera, to create labels for your problem. And so in that case, you would work in a semi-supervised space. Maybe you train with your labeled data, and then you move into your unlabeled data framework. With self-supervised learning, you can actually go ahead and leverage both supervised and unsupervised learning, where I might create classes for my data. So I can maybe use k-means clustering, create groups into my data, and then use those groups as my labels. Does that make sense? Right? So I can just kind of uncover hidden patterns and then use those as targets. And you might say, why would I want to do that? Well, it turns out for weather regimes, you can use k-means clustering first to create the weather regime dominant patterns over an area. And those are now your labels, which you can use to predict out into some future lead time, right? Other common terms that you'll hear me use here today and tomorrow include interpretable machine learning and explainable AI. And I wanted to note that these are distinct concepts. So interpretable machine learning refers to machine learning models that are in themselves relatively simple. So you as a human can look at a linear regression, y equals mx plus b, and you know if your m is large, that means your x makes a big change on y, right? So that is essentially what interpretable machine learning. Perhaps more relevant to us for deep learning, we need to turn to tools that allow us to interrogate that black box neural network. And for that, again, XAI. And so we can use things like feature importance or permutation feature importance, or we can shuffle specific variables one at a time, see how much our score or our error, let's say how much our error increases. And if it increases a lot when we shuffle a specific variable, we know that variable is really important, right? And so we can interpret that as being important to the prediction task. And I do want to mention reinforcement learning. I won't be talking about reinforcement learning beyond these two slides that you're going to see. Many of you have likely seen a robot movie. This is not a robot movie. This is Boston Dynamics. So this is a company that does robotics. And so for many of these robots, what's used is reinforcement learning. And so reinforcement learning is a bit different from the supervised, unsupervised, semi-supervised, et cetera, where in this case, we have a different framework where we essentially define a policy, and we want to make sure that the agent can learn to optimize that. And so more specifically, we break this up. For reinforcement learning, we would put an agent in some environment, and then that agent will interact with things in that environment. And after each action in that environment, it's going to do some sort of reward. It's going to get a reward signal, which we have to define. And then its ultimate, throughout the process, it's going to end up figuring out which actions lead to more rewards. So it's kind of like training a dog, right? It knows food, gets reward, keeps doing that, hopefully. The good thing, great. I will mention for reinforcement learning, it's not just robotics. A really important use for reinforcement learning for weather and climate, which again, the use cases are very limited right now, but an important use case is, for instance, in the US, they have used reinforcement learning for figuring out which walking pathways would lead to avoiding urban heat in cities, right? So you can envision this would be some sort of agent that's interacting with the environment, potentially something like evacuation routes could also be an important use case where you have an agent being the humans and taking some sort of action in some situation, which would be their environment. And now we've got some advantages and limitations. So we've talked about history and evolution of AI and different definitions. AI is not magic, but I'm going to tell you about the good things first. So some of the good things of AI is that we not only can make use of these very large data sets without having to predefine heuristics and thresholds ourselves, but it's also very flexible and allows us to use data of different modalities. Meaning if I have gridded data and I have point data, maybe from weather stations, I can merge the two much more easily without having to do anything complicated like data assimilation. Data assimilation is still very important, but what we can do then is we can now flatten the image into a one-dimensional vector, and I can stick the single point values to the end of it and feed it to a neural network and let the neural network deal with figuring out what's important or not, right? In a very simple case. Probably not the best approach, but you could. After you're done training, it's also very cheap to do inference. Unless you're dealing with diffusion, we'll talk about that tomorrow. And I guess going through some of these, you've heard about downscaling, which you'll have an activity for that task later today with Redwan. And But we can also do things like discovery and pattern detection, which is something that that my group has worked a lot on, and you'll hear about after the coffee break today. But there are a number of limitations that are really important to keep in mind. And this doesn't mean that you can't use AI for your task. If one of these is of huge concern to you, it just means you have to sort of keep in mind how to overcome these limitations, right? Or if you're presenting a model or using a model, keeping those limitations in mind and communicating those potential issues or caveats that that others that are taking that information should keep in mind. So of course, physics awareness is limited. You can address this by using physical constraints in your loss function and so forth. But it is limited out of the box if you're just using a pure data-driven approach. We really need good historical data. The more data, the better. Generalization can be an issue, not only to a changing climate, but also geographically, right? If I have a lot of data over North America, but I'm trying to predict over Madagascar, maybe it's not going to do well in Madagascar, which is a problem. How do I know that if I don't have a lot of data in Madagascar? There's other issues that many of you likely already know about. One of another challenge is that if I train a model to learn a physical parameterization scheme, and I want to stick it back into a physics-based model, that can be complicated if I'm using PyTorch, right? So we love using PyTorch, but putting it in Fortran is a little bit complicated. And there's ways to get around that. For instance, you could do knowledge distillation where you extract the equation or an approximation using something like equation discovery or, again, symbolic regression. So you get some mathematical representation, and that's easier to put in Fortran, but then you're losing skill. In terms of extrapolation, I just wanted to give an example of why this is so dangerous. Right, so we had this storm in Louisiana. So this was from the Gulf of Mexico, just southern parts of the US. And way up north in New York City, we had this happen. So this made landfall very, very far away, but a lot of the rain moved and produced this in New York City, far from where the storm made landfall, right? So these are the types of things we need to keep in mind when we're talking about generalization. How do we even address some of these unseen cases? Although those that are training very large NWP, numerical weather prediction models that are purely data-driven would argue we're actually seeing increasingly good performance. I also want to bring up ethics in AI. I do like to share this example from Face Depixelizer. This was back in 2020. So it's been 5 years now, probably gonna have to retire this slide. And I have heard from people who are fans of this tool, and they have told me that they fixed it. So, but my point isn't to call out this specific model. My point is to emphasize that if we don't have broad representation in our data sets, that leads to things like this occurring, where in this case, we have Barack Obama on the left-hand side. The task of the machine learning model is to increase the resolution. And even though this is probably one of the most recognizable figures, I don't know, in modern history, it still totally changed the person, right? And so for Face Depixelizer, okay, we all know who Barack Obama is. Maybe that Face Depixelizer didn't do much harm, but it can do a lot of harm when we're talking about weather extremes, right? To generalize to extremes, that means humans are impacted, right? That can be life or death. So figuring out after the fact, after deploying Face Depixelizer, it's not a big deal that maybe there was an ethical issue or some bias, but that is different when we're talking about weather and climate data. And so an example project where we are working on identifying, or we have worked on identifying biases is a project led by Professor Amy Quirkium. identifying places where Earth system science data in the US in terms of point weather observations is limited. Yeah, we noted that this can leak into our models, and I'm way over time, but just to emphasize that that machine learning is not causal out of the box. So I think someone had mentioned causality being of interest. And so really important that when we're using XAI, that does not mean that your machine learning model has identified causal relationships, and really important to keep in mind. I leave you with this slide, and I'll stop talking now.
Thank you for this really nice talk, Prof. Maybe we have time for one question from the audience here in the classroom, and then we will check for people that are online.
Hello, everyone. So thank you very much, Professor Maria, for your interesting presentation. I just would like to know how can we use large language models to interpret or to analyze climate variables or climate data sets?
Yeah, great question. So there are large multimodal models where they can take, and you've seen this probably with ChatGPT, like you can ask it to produce an image or produce a PowerPoint presentation. It did not do that for my PowerPoint presentation, but you can. And so for example, you can potentially fine tune one of these large multimodal models. There are some packages available that allow you to do this much more cheaply than having to fine tune the very, very large model itself. And so one project that we are working on or are going to be working on is taking in physics model data and writing out text to see if the model can interpret what's in the image or vice versa, right? Give it text and have it produce an image.
Thank you. Maybe one question online? Really? All right. Okay, so shortly, please.
Yeah. Because as type of like machine learning solving problems, so we got like predictions, classification, clustering, and all those things. But related to the LLM, we got their kind of like generations. So usually we use text because we got also diffusion models that are specialized in image and all those things. But specifically, when we talk about LLM, they use like text. But there are some techniques that we use, like we try to understand the observations like a text, so that we can learn the pattern between them and try to model and forecast. But these are techniques that people are working on. But for LLM, we use them just for generations, text and all documents.
Thank you.
Thank you for your nice presentation. I want to ask, what can you say about the impact of AI infrastructure on pollution and climate? I know that some countries are already trying to apply some techniques to maybe mitigate the impact of this infrastructure or adapt themselves. So, I saw some countries that are using the heat generated by the servers to maybe to use them in household during winters, some things like that.
Yeah, thank you for that great question, right? We're all excited about AI, but AI uses a lot of power, especially when we're thinking about large language models. I'm not an expert on the topic of leveraging, the energy component, but we did recently publish a paper on the use of large language models for education and research. And one of our sections included a discussion on the ethical implications for energy. And the reviewer suggested including discussion on how we can do knowledge distillation. So we can take a large language model and extract the specific underlying mathematical function that can help us with the tasks that we're specifically interested in, right? Because I may not really need a large language model to maybe analyze some like what it learned from weather or et cetera. And so those are things to keep in mind, but I know I have seen some headlines and news stories of also of countries or cities using data centers intelligently. But I will say from where I'm from, the state nearby next door is dealing with ramifications of these large data centers taking up energy, increasing costs, and using water resources. So ongoing issue that I think, yeah, we'll all need to grapple with. But I would say there's a lot of power in small models as well, and nothing wrong with using a small neural network.
Thank you. One last question from online attendees.
This one is mainly related to what everyone talked about. Is there any physical-based ML techniques in downscaling data? Can you kindly suggest something this? What we're actually talking
Yeah, Redwan will talk a bit more about that. So maybe do you want to?
Okay, so we take just one last question and then we go for coffee break. You will have the opportunity to continue the discussion, right? Okay, one last question.
Okay, thank you for your nice presentation. My question is about the model that you have used in production. And according to your experiences, what did you miss at the start that caused the problem later for your model? And for you, what is the most important for the model that you have used in your production, mainly in climate change?
Yeah, I guess I'll give a quick example. One of my first papers, or my first paper on using convolutional neural networks, I was asking the question as to how well can machine learning generalize in a changing climate, and specifically looking at convolutional neural networks' ability to do that. And so I had a really large data set of little thunderstorms. In fact, it's a data set that's in my convolutional neural network example, and which still needs some updates, by the way. I'm not done, but anyway, so those little storms, essentially the task was to classify, was it going to produce severe weather potentially or not? And I found it can do this very well, even in a future climate. And then I looked at some of the underlying data distributions a bit more, and it turned out that it can do this very well, probably because some of the variables didn't change a lot in the future climate. So then when we did permutation feature importance, it turned out that the importance of variables changed, whether it was in the past, like in the current climate or the future climate, which was really interesting to see. But I think that example is very specific to that classification task. It seems like generalization can be an issue for other tasks, especially if you have less data, right? So we had like over 1 million storms that we were able to leverage. So yeah, so caution. Yeah.
Let us thank again Prof. Maria. All right, so we have 15 minutes for coffee break and then we come back.
Yeah, any comments?
Yes.
Okay, I need coffee. Yeah.
I look for using Finland focus experiments. But my point is, for example, we like to focus the extreme events. I would like to have in the output just the extreme, not, for example, a classification, but I like to have a regression, continuous regression. I use my loss function. I add country regression, so country to, for example, 96-95% of my MSc that. Sorry. Yeah, to have in the output, but in the output, I don't have directly.
You don't have what?
In the output, for example, have, for example, the data, the forecast, but it's not specific. The percentage. No.
I don't understand.
That is my problem is I like to focus directly on the percentage.
Directly the
Yeah,
percentage?
yeah.
Percentage of what? Like
Yeah.
how extreme the thing is?
Some the 19%. But I don't know if you like, for example, to do the explaining physics modifies the loss function to integrate.
That's one way.
Yeah, to integrate, for example, the important for the important for example, the local. Sorry.
No worries.
The topography, yeah, the topography for the local in Senegal.
You're saying that the extreme precipitation is in the image that gets predicted is not sharp, like it's not realistic, it's too smooth,
Is
it's not extreme enough, because it gets
sous-estimation.
the what?
Is not, for example, the focus is 100 estimates, 100 coverage.
It's overfitting?
Yeah.
Yeah, I don't know. I think it sounds like a few different things. You're saying it's regression though, right? So for regression, if you're dealing with extremes, you could do
What mean my question? My question is, for example, these two methods if I use this, I have a problem for the output. And another method, I focus directly on the precipitation. After the precipitation, I calculate the percentage and I compare for the observation percentage I have. But this method is, for me, is not directly casting the extreme.
mhm.
Yeah, yeah. And the first
You're
method-
predicting the percentile.
Yeah.
Uh-huh.
The first method is predicting the first answer, but the second method is forecasting directly the precipitation, not percentage.
Image or point.
No image, especially
Image?
Yeah, yeah.
Okay, yeah. So for the first one, before quantile, if you wanted to not do quantile and you wanted to do just regression and not do the quantile, you could use this thing as your loss function. Have you heard of this?
Yeah.
You have?
Power
law? Power,
So,
what? No, don't look at that. Power law.
all that.
Power law. Power law loss
Loss
function.
function, yeah.
The power law loss function. Do you know?
Oh,
So this thing, it's kind of like for classification, if you have class imbalance, you increase the weight of the minority class, right?
it's for classification.
I'm trying to give you context.
Yeah.
You're not doing classification, but I'm giving you context.
Yeah.
So for classification, you would add weight to the minority class to make sure the model pays attention and does well on those, right? For regression, you could use power law loss function, which increases its attention on the extremes. Right, so for regression, for quantile, you could do a quantile. Yeah, I'm good.
Okay.
Quantile. I don't know if this is relevant to you, but you also want to make sure there's different ways to do your quantiles. But you're doing regression quantiles.
Regulation control.
Yeah, I would just try the power law thing. And then, oh yeah, and then the other thing you can look into. So. is if you have extremes, it may not do well, right? So to make it better spatially, you could use these different options like GradMag, Laplace, RMSE as a loss function, and then it'll help it learn the spatial gradients to make it sharp. Yeah, does that make sense? Yeah, and I'm happy to answer questions. I'm on this paper.
Yeah. Okay. I don't have my phone to see the title of your next presentation, so share first and then I will read from the screen. All right. Good. Welcome back, everyone. So we will continue the presentations with Prof. Maria, and she will present AI-driven weather forecasting and climate projection example applications. So, Prof. Maria, the floor is yours.
Thank you. All right, everyone, welcome back from coffee break. So we will be moving on now to the topic of specific example applications for AI weather forecasting and climate projections. So just a quick overview of what we'll talk about. So here I'll mention some AI methods for weather and climate modeling. I'm going to give you some very fast overviews of some projects using different learning methods, and supervised versus unsupervised and regression versus classification, just to kind of get your, hopefully, creativity flowing for how you can use it for your problems. And then lastly, some items on the horizon for my group specifically, but also so you can kind of get a feel for where people are going. And so I want to start off with a question since we just had break to kind of pull you back in, hopefully. So I want to ask, what would you prioritize out of this list if you had to only pick one to improve your model's performance? So we can raise our hand. I'm going to read them out. So would you use the latest AI architecture? Would you develop a better loss function? Would you leverage a better optimizer? So architecture, optimizer, loss function, or data size and quality? Who thinks it's the first one? Who thinks using the latest and greatest architecture will improve your skill? You vote for that. What about loss function? Better loss function. Loss function is important. Better optimizer. Better optimizer? No one? This is how you update your weights. And then finally, data size and quality. I see some folks in the chat voting for that one. And we've got, I think that's by far the winner here. Okay, great. I'm glad we're on the same page here because yes, data, right? And so, so this is an AI talk, but I did want to briefly start with this. So there are a number of different steps that have to be considered for data pre-processing. So how you handle missing data, how you handle the creation of your labels, any transformation, standardization, etc. Right? So you will have access to these slides that you can come back to because I don't want to spend too much time on this. But here is also a list of things that you should ask yourself, including how to encode your classes if you're dealing with classification, or what if you have class imbalance, even if you're dealing with regression. And another question that I often get asked is, how much data do I need? Which is a really complicated question, right? So unfortunately, there is no easy answer to that question, even though it's critical, but there is a rough rule of thumb here that was available from a Google training, which is about how many variables versus versus total samples. But now that we talked about how important data is, we can get back to the AI portion. So when we're thinking about where to use AI for weather and climate, I want to set the scene for the example workflow for traditional physics-based systems, weather or climate, right? You normally have your input state. I won't spend too much time on this because you heard talks about this, the data assimilation and so forth. Then you run the physics-based model. So you have now your Stokes equations, physical parameterizations, etc. You need high performance computing and you run forward in time. And then you get some output, right? So you have your prediction and then you're done. For machine learning, we can use machine learning or AI in any one of these states where we can, for the initial state, we can use AI for data assimilation. We can use it for parameter estimation. So some folks use this for estimating, for instance, which physical parameterizations would reduce or constrain uncertainty in the physics-based model, right? So this is all before even running a physics-based model. So some of you are concerned about the use of AI for weather or climate, and it's like, hey, you don't have to abandon your physics-based model. You can use AI to help you run that physics-based model better, hopefully. If you in the running the model state, you can also go ahead and use it to do a number of things. For instance, you can train physical parameterization schemes. That's an easy one. But you can also fully emulate or do online bias correction with your physics-based model. So maybe it has a bias and starts drifting as lead time increases. And so the AI model can be put into the physics-based model and it can be nudged back towards what is more true, right? So hopefully to remove some of those biases. And then at the output state, we can use AI for a number of other things, including downscaling and upscaling. And we can also use AI to completely forget about the physics-based model. For those of you who are ready to dump your Fortran weather climate model, you can just go ahead and train an AI model to predict forward in time. And we've seen a lot of things. I think someone during the coffee break mentioned GraphCast to me. So that would be an example of a system that completely bypasses this. Something that I've heard also quite a bit throughout the last couple of days with you all is the issue of data scarcity or very little data for your problems, right? So it's really hard to get data. It's really expensive to get data. People don't let you get data. And so I just want to mention that there is a spectrum that you can work with machine learning. So if you have very limited data, you can use tools that are more robust to small data sets, right? So for instance, symbolic regression, I put this link here. There's this Python package for equation discovery called PySR. It's open access. It's super easy to run. It actually has Julia and Python. And this works well if you have little data. If you had a lot of data, it's actually bad. So this would help you find some sort of machine learning-based equation. In the middle, where you have moderate data, you can use a physics-informed neural network. So this would help your neural network not sort of diverge very far away from reality. And this would involve either putting some physics in your loss function, which I was talking to someone during the break about, or you can put equations into your architecture. And you can also figure out closures for equations, right, to reduce error and so forth. And then if you have a lot of data, of course, neural networks are great. If you have a lot of data in one setting, but very little data in a different setting, there are things you can do. You can train where you have a lot of data, so maybe era 5, right? We all have a lot of global data era 5, whether it's trustworthy or not, everywhere is questionable, but and for all variables, of course. But we can train where we have a lot of data, and then we can transfer learn or fine tune in a situation where we have a little bit of data. So we have less training to do, hopefully, right? And meta learning is another approach as well that we can use to go from where we have abundant data to less data. All right, so some specifics here because we are going to need this language when we're going through the examples. When we're talking about regression, we're talking about prediction of continuous data. And so some examples of continuous data includes predicting tropical cyclone maximum winds, right? So if we're predicting tropical cyclones in Madagascar, or if we have maximum land surface temperature in an urban area, that would be a regression task. If we are doing prediction of cloud coverage, that would be important, or prediction of the percentile of precipitation. That would be an example of a regression task, right? And also for bias correction, you would need regression. For classification, we're talking about discrete groups of data. And in this case, there are many examples as well. So here are some examples. I've already given you the example of a thunderstorm with severe hazards, but we can also think about type of cloud that is in a photograph. So this doesn't even have to be traditional physics model output data. You can also think of images. So we had a project with NASA that we wanted to get funding for. We didn't get it, but we wanted to leverage many photographs from a citizen science project that people had apps for, took photos of, uploaded them to this NASA database. The database still exists, so maybe we could still do the project. But then we can think of training a machine learning model to look at the images and then predict what that cloud is. How would you decide what model to use? And this is just in supervised versus unsupervised, right? So we do have a spectrum with semi or self-supervised. But for supervised, there's a lot of decisions we need to make, right? So do you have labels? That's when you know you have supervised learning. But whether it's regression or classification, whether you're deterministic or probabilistic, and whether you have single value, image, or time series. All of those are key points in your decision-making process as far as which model are you going to use. And then if you're thinking about unsupervised, this would be clustering, dimensionality reduction. So I think Jonathan had mentioned principal component analysis. You can also use autoencoders. There's a range of different complexity for dimensionality reduction, and also reconstructions using like synthetic data generation, for instance. And then if we think about the nature of our labels, this is for supervised learning, this would be a really a space where you can either work in a specific sort of habitat of neural networks, or you can even blend some of these types of neural networks. So for instance, if you're dealing with a single value, that's when you would use something like a fully connected neural network. If you have images, convolutional neural network would be a great approach because it reduces the amount of total weights, and you learn shared patterns around the image, right? Hopefully making your model more robust. And if you have time series or language, then you would use some sort of temporal model like a recurrent neural network, or more fancy things like LSTMs or transformers. And of course, there are CNN LSTMs or vision transformers or so forth. So there are combinations of these. They're not totally exclusive. You can have a time series image problem. So some quick examples. So I'll start with supervised learning. So we have this project from NASA where we are tasked with taking their physics-based model and estimating. So this is an estimation task. We have to, not prediction task. So we're estimating how much lightning or where lightning is occurring, within the physics-based model. So this is the NASA GEOS model. So currently the way to estimate lightning has some deficiencies. And so we went ahead and trained a UNet, which you'll be using with Redwan's downscaling example to estimate flash intensity. And we also did this for total flashes. Actually, this is total predicted flashes and total actual flashes. So for total flashes, it turns out it can do pretty well. It can do, in some cases, better than the established methods. And so we have a supervised learning task where in goes the NASA GEOS meteorological fields. We're also using aerosol data because it turns out that's really important for the composition of the thunderstorm and what produces lightning, like ice properties. And then it outputs an image where it thinks there's lightning and how much. So in fact, in this image, the gray is the actual from the geostationary lightning mapper, an instrument on board GOES, a geostationary satellite. And the contours, you can ignore the blue, they're just zeros. The contours are the predicted from the UNet. We can also use it for feature detection. So here is an image of a UNet, and a UNet takes in images, downsamples them or makes them coarser, and then makes them finer resolution again, back to the original size. Or you can keep going if you want to make it higher resolution. And there's also skip connections to allow the learning information to get back propagated towards earlier layers and resolve some of these original vanishing gradient issues from the earlier days of deep learning. And in this case, a UNet was basically built to detect objects in images. And it turns out it can do that really well for physics-based data. So in this case, we have a mesoscale convective system. So an organized thunderstorm. We had some labels over North America, and we gave it era 5 in this case, so reanalysis, and it could predict where there was an object that was a mesoscale convective system. A quick example of taking a case where we had a lot of data and then trying to extrapolate to an area where we didn't have data is in this paper. We don't focus on that because this is an intercomparison of methods, and ours is the only deep learning method in this intercomparison. But what we did for global detection of mesoscale convective systems is we did some data augmentation techniques, like something as simple as flipping the input image can suddenly help your model perform better if you're giving it data in the Southern Hemisphere. Yeah, we started like 15 minutes late. So you can flip the image if, for example, to help it Northern Hemisphere, Southern Hemisphere type things. And of course, you can still, that's a really simple example, but you can get creative. I'm going to leave this one for tomorrow since we are short on time. We can also do something as simple as unsupervised learning using k-means clustering to identify weather regimes. So here we're in an unsupervised learning setting, and I can train it using reanalysis or observations, and then I can apply it to a model to evaluate the physics-based model, right? So here I'm comparing reanalysis weather regime frequency, and you can see that the community Earth system model, this is a subseasonal prediction version, has biases as lead time increases. So you can use unsupervised learning, train in observations, and then use it to evaluate your physics-based system. For signal extraction, here, Kyle Ha, who's a student in my group, PhD student, he went ahead and asked a long-standing question, which is the El Nino Southern Oscillation and decadal variability actually two separate mechanisms, or is ENSO just, or is a decadal variability just a residual of ENSO? And it turns out he took an autoencoder, an unsupervised learning tool for reconstructions of images, and modified the loss function so that it can separate spectral properties, and it disentangled decadal from interannual variability on its own. And likewise, Emily Wazinski and other students, she used a specific case of a autoencoder, which again is for reconstruction, unsupervised, and she used a generative version of it, which is a variational autoencoder that uses a KL divergence term as a regularizer in the loss function. And she was able to, within the bottleneck or latent space of the autoencoder, characterize ENSO diversity. So you can extract the reduced dimensionality information in an autoencoder and then explore things with it. Again, quickly, Alice Duvivier, a collaborator at NCAR, she went ahead and had a question, which is, polynyas are really difficult to characterize with heuristics or thresholds in Antarctica. If you don't know what a polynya is, it's okay. I did not know what it was until Alice wanted to work on this. She gave data to a self-organizing map algorithm to detect areas where ice moved away from the coast, because that's really important for biological things. And then we looked at trends, and it turns out that certain patterns of polynyas are decreasing in future climate projections. Jairon, another PhD student, used machine learning to test whether this schematic out here for subseasonal prediction sources of predictability held for weather regimes. And he created different XGBoost tree-based models with atmosphere, land, and ocean as inputs. And he found that that schematic can differ based on the weather regime you're predicting and the season. So, so you can also use machine learning to go ahead and ask some of these questions and put them to the test and see if they really hold. So things we're working on include an AI-ready data set to support fast iteration with AI, including causality in our analyses, and multimodal data consideration, including not only text to image, but also societal data into our frameworks. I want to mention continued training is a top priority for me, especially at the intersection of AI and geoscience in the US and internationally here. Thank you for having me. And because it's critical that we have folks working together in both computer science and the domain science to catch little subtle errors, like me asking ChatGPT something about the frost point temperature and it got it wrong, and uncovering biases. Like here, we asked DALL-E, what is an illustration of a meteorologist at work? And I'll tell you right now, NOAA does not have this much money. Okay, so with that, I'll go ahead and stop. Thank you so much for your attention. I look forward to continuing to work with you tomorrow.
Thank you again for the nice presentation. So we just have time for one question.
Okay, so my question is, how can we handle the data drift in the climate modeling? For example, we can predict the weather on a daily basis, but when an abnormal event such as a cyclone occurs, the model may struggle because it has not seen such extreme condition before. So how can we prevent the model from degrading in this kind of situation?
Yeah, so I think I spoke to someone earlier about including in regression-based tasks when we're dealing with extremes. We can do things like a power law in our loss function, where we increase the weight of extremes in a distribution. This would be for a regression type problem. For the physics-based models, we're seeing increasingly good performance out of models like GenCast or even the latest iteration from DeepMind on tropical cyclone prediction. And that's purely data-driven. And I would say probably because we're including like generative capabilities and they have a lot of samples. So even though it's daily short-term data and you're concerned about climate change, they seem to be learning some underlying physics or something from the data and are performing pretty well. So I think this has become a little bit less of a concern than it was a few years ago, given the really increasingly good performance. But that said, I would still continue to stay alert, right? We maybe for tropical cyclones, they have a coherent structure, and that might be easier for the model to perform well in or predict. But if you're dealing with extreme scenarios like rapid intensification and so forth, I mean, we always want to keep evaluating and keep improving. So yeah.
We are running out of time, so
So I mean, the AI models being able to capture the features doesn't mean they are learning underlying physics. Is that, I mean, it's just a pattern recognitions, or it is there you can kind of derive some kind of physics, like Navier-Stokes or thermodynamic equations.
Yeah, I mean, I think ultimately any model, we know all models are going to be wrong, right? All models are wrong, some are useful. So it depends on what is important to you. If you really care about mass conservation, which, I mean, yeah, we should care about it, but but maybe then you want to make sure you're using a model that performs well in on those objectives that you care about or those metrics. If you are doing impacts, right? Or if you're doing some other task where the model is performing super well, but maybe it just doesn't conserve mass very well, but it's doing well for your task, then I would argue in that case, it's performing well for your subset of metrics. So it just depends, right? We can't expect one model to do well on everything. The ability of AI to be able to focus in and drill down on the specific question and task that you care about is sort of what I would focus on, as opposed to, to more holistic total evaluation.
okay, so the last question, because I give you the opportunity to ask questions, so I will give you the opportunity to ask your question as well.
So I would like to know what are the recommended architectures from statistical AI that we can use for analyzing climate problematics. For example, predicting temperature or other applications. What are the recommended architectures from statistical AI?
Yeah, so I think it'll ultimately depend on like that tree I showed of decisions that you have to make based on whether it's image-based, point-based, or time series-based, right? And then go from there. So if you're dealing with you want to emulate some physics-based climate model and it's forward evolution, then it's going to need time series and an ability to update its memory. So like a recurrent architecture and also an image architecture, where in that case, you might want to use a vision transformer if you have large data, or a simpler model if you have less data. But I'm also happy to chat with you about your problem specifically offline.
All right, thank you. So let us just thank again the speaker. Thank you, Prof. Maria. So we're gonna move to the next speaker, Cedric. Cedric, can you hear us?
Yeah. Can you hear me too?
Yes, we can hear you. Can you please share your slide?
Yeah, of course. Can you allow me to share, please?
Yeah, sure.
Yeah. So just wait a moment. Can you see my screen? On
Yes, we can see
is
your
it okay?
screen. Yes, thank you. All right, so we will continue with the next speaker, who is, yes, Cedric. He's from France. I think he can also introduce himself before starting the talk, and he will be presenting monitoring and subseasonal predictability of heat waves in West African cities over recent decades. So, Cedric, you have the floor.
Okay, thank you. Hello, everyone. My name is Cédric Languet. I'm actually work as a postdoc at Laboratoire des sciences du climat et de l'environnement in France. And previously, I am also an EMS alumni. I do the Master Cop at EMS Hambourg in 2016 or 17, I think so. So today, my talk will be on the monitoring and subseasonal predictability of heat wave in West African city. So, and also thank the organizer for give me this opportunity to contribute to this workshop. About the contents, we all know that the red planet is actually getting more warming, and due mostly to anthropogenic greenhouse emission. And this analysis from the NASA, which actually shows that more everywhere over the planet, the anomaly of temperature is actually positive, which can confirm this warming trend. And when it's come to Senegal, this diagram stripes is actually showing the evolution of temperature over Dakar in Senegal since 1874. And what we can see that across the recent, across the year 20s, we observe actually an increase in temperature, which actually an increase in temperature, which actually showing that that the warming is actually effective everywhere in the planet. So under this warming condition, extreme heat wave will become more frequent and also increase in intensity. And such extreme event which can occur in West Africa can also occur everywhere, but mostly we will focus here on heat extreme event. This analysis from the UNICEF is actually revealing that Africa during the period 2000 and 2020 has experiences at least 4 to 10 heat wave, 4 to 10 heat wave with different intensity from moderate to extreme severe. And this event pose a severe threat in human activity and human health, and can also cause some death among the vulnerable population, mostly the elderly and the children. Some research projects have been carried out in the region in order to advance knowledge on heatwave in West Africa. For example, we have the ACASIS project, which have been launched during the period 2014 and 2020 and 2018, which focus mostly on the detection and the physical driver mechanisms which control actually heat wave in West Africa, in the Sahel region, and their predictability. And we also have the NR Steward project, which was launched during the period 2013 and 2024, which aims to build an hailing alert system in order to alert and prevent population about the occurrence of extreme rainfall, drought, heat wave, and thus in the West African city. So, given this, given the damages caused by this type of heat wave, we can see that it is a major concern in the scientific into the scientific community. So today my talk will be organized in two parts. The first part, we talk about the monitoring of heat wave in West Africa over the recent decade. And the second part will be mostly about the subzonal predictability of those events. And this work has been done within the framework of the NRT World Project. So I will present briefly the West African climate because some previous talk has already introduced the West African mousson, so I will not go too more in detail here, just some brief information. So the West African region can be subdivided in two parts. We have the Sahel, which is characterized by the hot and dry climate, and we also have the Guinea region, which is characterized by a hot and wet climate. And the population activities in the West African region are mostly dominated by the rain-fed agriculture and breeding, which are conditioned by climate conditions, which are controlled by the West African mousson. So we need to more be adapt or more have strong knowledge about the West African climate in order to be well adapt about their activities. So the data that I will use for the monitoring of heat wave, we will focus on two specific heat wave. You have the dry heat wave and the wet heat wave. The dry heat wave is the one that happens without air humidity, and the wet heat wave is the one that happens with humidity, and that one is more dangerous for the population and their health. So for the monitoring of dry heat wave, we will use true meter temperature, and for the humidity, for the monitoring of dry heat wave, we will use a combination of true meter temperature, relative humidity, and wind speed. And the data that I will use is mostly RFF and MERA analysis over the period 1993 and 2020. So for this talk, I will just present the result obtained with RFF analysis. And the data are early data, and we focus on minimum and maximum daily value. About heat wave, I will give the definition and the detection process. So heat wave is defined as a period of at least 3 consecutive days where we registered temperature over a given threshold. So sometimes in the literature, we are using the 90 percentile as the threshold to detect a heat wave. And as an indicator, as I mentioned before, I will use 2 meter temperature. I will use a Weber temperature. I will use apparent temperature. I also will use the universal thermal comfort index. About the detection, so this plot is actually show what is actually described in the algorithm. So this plot, if we take the case of the maximum temperature, can you show my mouse, please? If you take the case of the maximum temperature, we have the solid red curve is actually represent the evolution of the 19 climatological daily percentile computed over the period of study, and we have the time series of the daily evolution of Tmax, for example, and we will consider a heat wave where when 3 days will be above, when 3 consecutive days will be above the climatological percentile. And we also do so for the minimum temperature. So we have the blue dot line and the blue solid line. And the last type of heat wave that we focus on it is the concomitant heat wave. So it's the heat wave which occur during when the maximum and minimum value together at the same time during the same day are above the threshold. So we call them concomitant heat wave, and we will see that that type of heat wave are very dangerous also for population, because we don't have the time to relax during the night when it is too hot during the day. So I will show you some results when apply this detection algorithm over the West African region. So actually, we use a different indicator, and this map is actually shows the distribution of heat wave occurrence over the West African region when we use actually the minimum value of this indicator. So this type of heat waves occur mostly in the night. So I will call them nighttime heat waves. So what we can see that is over the coastal region, we have a lot of occurrence of nighttime heat waves. This because we have an advection of humidity coming from the Atlantic Ocean. And when we look actually at what is going on with the wellbot temperature, we can see that we have the highest occurrence compared to the other indicator. This because the wellbot temperature is actually integrate more humidity. And when we also look actually what is going on, and when we also look what is going on actually with the maximum value of the indicator, compared to the previous distribution, we can see that for the maximum indicator value, the distribution of the heatwave occurrence is actually more uniform. And the region which is more affected is the Sahel, the north of the Sahel, and the Sahara Desert, which is not surprising because we have a lot of heat there compared to the coastal region, to the Guinean region. And when look actually on two meta temperature and the apparent temperature, we can notice that the distribution are more close, which is not surprising at all. And finally, I show the result with. Can you hear me? Finally, when looking at okay, nice. Finally, when looking at the heat wave type 3, so the concomitant heat wave, you can see that compared to the nighttime and daytime heat wave, the concomitant heat wave have less occurrence. This is not too surprising too, because they are too much restrictive, because the condition is that they occur at the same time during the day and during the night. And when looking also on the wet bulb temperature, we showed more occurrence over the Sahara region, and this is not. This is also related to the occurrence that we have registered during that you have registered on the previous analysis. So this analysis also permit to highlight some different uncertainty when detect a heat wave. So when detected heat wave, we can have the first source of uncertainty, which is the indicator to use. So when we compare the different indicator, we can see that we have uncertainties from one indicator to another. And the second source of uncertainty here is also the definition that we use. Are we actually focusing on the nighttime heat wave or the daytime heat wave? That is also some choice that must be done before processing heat wave detection. And the last source of uncertainty that have been also highlighted by some previous study is about the data. So the distribution or the heat wave occurrence is not similar when I use MERA analysis that I didn't show it in this study. After investigating the heat wave over the recent decade, we now focus on West African city, because the previous result that I showed was generally over the West Africa region. So I will try to focus now on some cities. So these are the cities that I'm focused on in this study, and these cities have been subdivided in some block according to a previous study such as Moron et al. So we have the continental block is formed by cities which are on the continent part, and we have the Atlantic block, which is formed by cities which are located around the Atlantic coast, and we have also the Guinean region, which the Guinean block, which is formed by the cities which are located actually over the Guinean coast. So in this talk, I will just focusing on what is actually going on in the Guinean region with the minimum value of temperature. So this first analysis, I show the evolution of the occurrence of the days in heat wave when using a minimum value of the three indicators, which are the 2-meter temperature, the wet bulb temperature, and the apparent temperature. So what we can see here is we have an increase actually over the last decade of heat wave occurrence in the Guinean region. And we can also notice some peaks of heat wave during a given days. So we have during given years. So we have the year 1998, 2005, 2010, 2016, 2019, and 2020. And this specific year are actually year where we registered a strong El Nino event. So we can expect some link between actually heat wave in the Guinean region and the El Nino event. And we will try to investigate in more detail this link. And we also noticed that nighttime heat wave associated to wet bulb temperature are very persistent compared to heat wave associated to 2-meter temperature and apparent temperature. And this is what I have said before. We have a reinforcement of heat wave over the last decade. So now we will try to see what is actually going on during the year where we registered the peak of occurrence in heat wave and the SST anomaly. So we try to see what is actually going on. We compute actually the anomaly of SST during the day where we registered the heat wave for the given year. So we have this composite, and this figure is actually shown on the x-axis, the percentage of heat wave days for each year, and in y-axis we have the anomaly of SST. So what we can see is that 5 over the 6 years where we registered actually peaks of heat wave are associated with associated with positive anomaly of SST, which actually show the influence of the El Nino oscillation. And what is actually interesting is that the year 2016 is associated with negative anomaly of SST. This means that we have other processes that come into play and which tend to reinforce heat wave during this particular year. And this result is also coherent with some previous work, notably Moron et al. In 2016. So after this investigation of the link between the El Nino phenomena and the heat wave, we also make a little bit some classification analysis based on the duration of heat wave. So we have computed the duration actually of all the heat wave that we registered in the Guinean region, and we'll classify it by class. We have classes from 3 days to 30 days. And we found that half of the heat wave are lasting actually for 3 days. And around 35% and last for 4 to 6 days. And the more dangerous heat wave, around 8%, actually last over several days up to 30 days. In summary, for this analysis, we can say that frequent heat waves that occur actually in the Guinea region can last up to 6 days. So after this first part on the monitoring, I will focus now on the predictability of heat wave. For the predictability of the heat wave, we'll change or we add some subseasonal to seasonal forecast model. We have the ENS extent forecast range from ACMWF, and we have also the UKMO. And this analysis is actually carried out over the period from 2001 and to 2020, and we focus also on daily minimum and maximum value of this indicator. And for the valid evaluation of the model, we will use the RF5 reanalysis. So, as Dr. Morisol told this morning, when it comes to the evaluation of the model, we will use some metrics depending on which type of forecast we are dealing with. Sometimes we have probability forecast or we have deterministic forecast. In our case, we have probability forecast. So we use a probability score. In our case, we will use a dichotomous score. So considering this contingent table, we will try to compute the hit rate, the false alarm ratio, and the Gibel score. The Gibel score is a little bit different because it accounts for the probability of detection of event without random chance. So we want to see if the model is actually reliable. And when for the evaluation of the model, we proceed actually differently because we subdivide the analysis by season from winter to autumn. And we also focus on the evaluation of the model from medium range forecast to long-term range forecast. The medium range forecast here is the forecast up to week 2, and the long-term range forecast is forecast up to week 5. And in this graph, the rectangle with cyan border and represent actually the heat rate compute with ACMWF, and the rectangle with black border represent the heat rate compute with the UKMO model. And the red line is actually the climatology. And for the heat rate, the closer from one it is, the better is it. The beta is the model. So what we can see is that compared to the climatology, the heat wave is actually compared to the climatology, the heat wave is actually higher, which actually show that the model are able to forecast hot days, so the days are part of heat waves. And when we we look at the evolution of the heat wave for the ACMWF model, we can see that we have a gradual decreases in predictability from winter to autumn. And when we compare the two models, we can see that the ACMWF model is actually better perform for medium range forecast up to week 2, but when it comes for long-term forecast, the UKMO outperform the ACMWF model. So that is very interesting because each model has its own specificity. There is not a good model and a bad model, but according to what we are going to according to what you are looking for, one model can be done the task better than other one, but it's not a good and a bad model. And when it comes for the false alarm ratio, we can see that the false alarm ratio, even for week 2, is actually higher. It means that the model actually overestimate hot days compared to era 5. And we also we also try to make some investigation on the potential of machine learning in order to correct forecast model. So we'll try to use these 3 models. You have the random forest, the balanced random forest, and the support vector machine. And we use as input anomaly of 2-meter temperature forecast. The goal was to make a bias correction of the subseasonal forecast. And we have divided the period of study in 2. We have the trend set and the test set, and the metric for evaluation is the F1 score. So I didn't show the result, the intercomparison between the 3 methods, but the balanced random forest outperform the classical random forest and the super vector machine. I use the term balanced random forest because I have a case of imbalance data set. So I apply some smooth methodology to balance the random set before applying the random forest algorithm. And I try also to compare what is actually going on between the balanced random forest and the SMWF model with respect to era 5. So what I'm doing is over the test period, I try to simulate actually the evolution of hot days in era 5 and also in SMWF and also for the balanced random forest, and try to compute the same score. So the hit score and the false alarm ratio. Compared to the SMWF, we can see that the balanced random forest perform very well. And we can also note good improvement on detection up to week 6. And when it comes to the false alarm rate, we can see that we don't have a lot of improvement. The false alarm rate remain very higher for short lead times. And the false alarm rate rely.
Sorry, you have just 2 minutes.
Yeah, I'm all this. It is almost the end of my presentation. So we don't have we have improved significant improvement in the predictability of heat wave with the machine learning method, but we don't have an improvement on the false alarm rate. So as a summary for this analysis, for this study on this presentation, we can retain that we have a source of uncertainty when in heat wave detection, that at mostly the threshold that will be used, the indicator, the methodology, and the data. And as the driver of heat wave over coastal region, we can think about El Nino influences, and also we have the influence also of humidity coming from the Atlantic Ocean. And about the predictability, we can retain that the model, the subseasonal forecast model, shows scales up to 2 weeks, but the false alarm rate remain very high. And we can also gain some improvement when using machine learning algorithm. But also we have this challenge of higher value of false alarm rate. So I will stop here because of time. Thank you for your kind attention.
Thank you very much, Dr. Cedric. Thank you. So we will quickly move to the next speaker. Since he will be in the panel discussion, you will have the opportunity to ask your question. Okay, thank you very much, Dr. Cedric. And yes, a round of applause for him again. All right, so the next speaker, please, Dr. Cheikh Fall. Do you have Cheikh? Oh, Cheikh is here physically. Great. All right. Okay. Let me introduce you first.
Yes. Okay.
So you don't need to stop sharing.
Yeah, Cedric, can you stop sharing?
Dr. Cedric, can you stop sharing, please? Thank you.
Now we download it and then. Oh, yeah, sorry. First we download, this is PPTX, right? Yes. Okay. Then now compatibility issues. No, it shouldn't be a problem. I have to share first. Share screen first. Share your screen. Okay. Yeah. 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 And
All right, so let us welcome the next speaker, Cheikh Modou Noureini Fall. All right, and he will be presenting African monsoon circulation. Oh, can you go to the title? Okay, processes and impacts on society. Welcome, Cheikh, and you have the floor.
Thank you very much. Thank you for this opportunity. Thank you for this opportunity. So you will change the slide for me? Okay. Thank you for this opportunity to share our work with you. So this talk is titled by first slide, please. By the African monsoon circulation process and impact on society. So go ahead. Yeah. So we will try to follow this outline. Firstly, we will talk about the water cycle and global warming. Then, for the impact on the West African monsoon, its drivers and variability, and the scientific challenge on this area, West Africa, globally, and the impact from regional to local scale, and the impact on socio-economic activities. And here we will make a special focus on the agriculture in Senegal. So go ahead, yeah. So in this slide, we show you here the anomaly temperature from 6 data set. It is mainly rare analysis data. So you have HERA5, you have GERAS, and you have some observation like CRU and NOAA global temperature. So what we can find here is just we have a increase, a constant increase of the temperature since 1980. So we can see here, and it is not model, it is just observation. So this warming has many impacts, and it turned to accelerate the water cycle by increasing its water holding capacity. So, and we have some consequence on extreme events in Africa. Okay, so here you have a schematic representation of the water cycle. So you have the evapotranspiration here, the rainfall. It is very simplest schematic for the global conceptualization of the water cycle. And here you have the Clausius-Clapeyron equation. And what this figure result is that if we have an increase of temperature in the atmosphere, we will have an acceleration of the water cycle, and that yield to the increase of extreme events in the global scale, and in the regional we can have some impact on society. Okay, we have to. Okay, so here about the extreme events on the Sahelian, you have three panel. So here we have just the annual rainfall. Here we have the contribution of extreme events to annual rainfall. And here we have the temperature, like the first figure. And what we can see is in the Sahel, we have a drought signal between 1970 until the beginning of the 2000 years. And you can see that we can't reach the level before the great drought in the Sahel. But if we take a look on the extreme events, we can see that for the extreme events, we already reached the level before the great drought. So we have so now the rainy season that we have in this area is modulated by the extreme events. So, okay, and the consequence you can see here with this figure about the MDAT database. We have many consequences of extreme events. You have earthquake, you have storm, you have extreme temperature and flood, and you can see that since between 21 until 2020, we have an increase of number of deaths from these extreme events. Okay. Yeah. So here you have always we are in the context. So if we can't resume this situation, we will have more flood in the future and more drought at the same time. Because when we have a rainy season with a chaotic behavior, we can have more dry spell, more long dry spell that result to a drought here. And if we rain, we can have a more extreme events when we get a rain. Okay, so now how we can understand, we can get to better understand this situation. So we have in this area, we have the West African monsoon. Many of the previous lectures has already talked about that. So you have here the drivers of the West African monsoon. You have the African easterly jet, you have the Saharan heat low, you have the, how do you say, the tropical easterly jet too. And here you have the African easterly wave who carry out all the mesoscale convective system in the area and provide around 70% of the rainfall in the area. And the intensity and position of the warm driver is influence the amount of rainfall, but also its variability. So it is important to better understand all these drivers, and so we can try to predict these extreme events. Okay, so maybe we can skip this, go directly here. Okay, so here what we have as a scientific challenge in this area. So for all model from the GCM model show us this dipole in the Sahel. So in the central Sahel, we will experience more rainfall. So here you have the anomaly of rainfall. And in the western Sahel, we will have less rainfall. And it is you can see that we have a spatial variability of these two patterns. And if we take a look here, you can see that this decrease of rainfall in the western Sahel is modulated by what we call it the false start of the rainy season. So here you have in x-axis, you have the month, and here you have the anomaly. So you can see that the first rain will decrease. Why? When we will, at the head of the African monsoon, we can have an increase of rainfall. So it is always the same. We will have more dry spell and more extreme events in the same rainy season. So, and we have an impact. So we have you see this Sahelian dipole. And in terms of impact, so here you have the crop yield. So you have the crop yield in y-axis. And what we see, you have here the Western Sahel, and here the Central Sahel, and the whole Sahel. So we can see that the impact on crop yield will be more important compared to the Central Sahel. And if you see here, we have Nigeria, Mali, Burkina Faso, Senegal, and West Africa. You can see that country like Senegal will be experience high decrease of yield of crop yield in the future. Okay. always we are in the challenge. So what is the main challenge here? And we discussed about that yesterday. We have the gap about the density of the network observation. So here you have the distribution of all the network in the globe. So you can see that at the CONUS or in Europe, you have a high density of rain gauge or of network observation. But in Africa, you can see that we have almost nothing. So that is a big challenge for the researchers to understand what will be how do you say, what will the climate, what will be the behavior of the climate in the future. And here we use, as you know, several data sets from the remote sensing like GPCP, TRIM, CMORPH, TAMSAT, SHIP. Because as you know, this is a big problem. But yeah, once for the model, we can't reach a good result here in this area. And also, to put in place a good study on impact, it is very difficult to do that. Yeah. And here you can see that we have also some successful situation, some successful experience. For example, in the next slide, if you go there. Okay, so here we have the DACI network observation. It is a collaboration between the University of Dakar and the University of Potsdam, who try to understand the path of the mesoscale convective system, and they have a high density network here around in the western of Senegal. And you can see all these yellow point is the different stations that we have. Go ahead. Okay, and here we have also another how do you say, another effort. Yeah, it is a very local effort, but with UCM, University of Madrid, and we try here. You have what we call it this disdrometer. We can go until the drop square of the rainfall. Then we can have many variables like the velocity, the drop size of the rainfall, and we can try to understand the fingerprints of the mesoscale part of the system or the stratiform part of the system. Okay, so here it is always the same. We try to understand the extreme events that we can have. Here we have a big storm at 29 August in 2023, and you can see here you have the humidity and the rain, and here you have the temperature. And the signal is very important, because you can see that you have a brutal decrease of the rainfall, and that is a fingerprint of the remotely system that we can from the east of Senegal. And here also for the humidity, you can see when we have this peak of the rainfall, you see that we have a brutal decrease of the humidity relative, and it is a fingerprint, and we can try to follow this kind of signal in the model or in our future observation. Okay, so here I just listed some to resume the different challenges that we have with modeling and forecasting time. To improve model performance, we need to improve the handling of tropical process and with the system in the model, advancing ensemble modeling and apply convexity permitting model with an African lens, and also to try to see about the K-scale modeling in this area, because we don't have, it is poor for the moment to have some result about the scale. Okay, so we can. Okay, so now maybe we can talk with you about the impact on the society. And here, as I say, we will just focus on the agriculture sector. And in Senegal, as you know, this sector contributes almost 10% on the national GDP. And it is very important. Many people live on agriculture. And the reduction it is not just the climate, but we have also the soil fertility, and we have also the loss of nutrient around 40 kilogram per hectare could lead to a total deterioration in the agriculture production base and 30% loss in cereal production in 25. And we can continue about that. So go ahead, please. Yeah. So here what we did in the x-axis, you have just the rainy season. You have the agronomic season here from 1st to June, to end. From 1st of June to end at okay, from 1st of June to end October. And here you have some extreme events. So here you have a dry spell, long dry spell 20. You have the dry spell short, dry spell long 2. You have some wet spell, the wet extreme events. So you have dry extreme events here, and you have wet extreme events. And here you have some traditional indicator like SPI, like solar radiation, and NDVI. So, and here you have the relation between these indices and the crop yield. So if you see the DSC, you see that their performance is better in July. While for the DSXL, we can see that they can perform even in the beginning of June. So this indicator is a great indicator for the false start, which we call it the false start. When we have rain and you think that the season is started, and now you have it is followed by a long dry spell. So here, and maybe some indicator like the the dry spell short, they can impact positively on the yield. Okay, so and this figure can complete this one. So you have in the x-axis you have the agronomic season, and here you have your R square to follow the performance of the model, and you can see that we can have an idea about crop yield. At September, we can have how the yield will if we will have more yield or less yield in this area. Okay. So, and here we present you the research program of the National Adaptation Plan, because the government of Senegal launched this program in 2022. And the idea is to make in place 3 consortiums, which call it consortium. And for the climate model scenario, the consortium was led by national agency, by l'ANACIM. And for the agriculture system, we have ISRA, it is the Agronomic Institute of Senegal. And for the health consortium, we have the Ministry of Health. And for the food consortium, you have the food institution. And here it is the beginning of the program and the end of the program. And it was a very interesting program because we have a bottom-up approach from the research to the end users. And we will exchange about result, about methodology, and it was very interesting. And we have some interesting result. We can go slide. Yeah. So here, about this program, we did that. Here we show you 32 CEMIP model in Senegal. No bias corrected. So we can see that we have big difference between model. And I add also ERA5, it is a rare analysis data, and SHIRP, which is a satellite data. So this parameter is just the rainfall. So you can see that for some model, we have more rain, and for other model, we have less rain. So it is also the problem with the CEMIP 6 model. So it is another indices, it is a CDD. So it is the same. We can have a big variation between the models. And here we can see SHIRP, which we can consider as our reference. And here you have ERA5. Okay, go. Next. Okay, so here we have the agronomic start of the rainy season by using Shivakuma criteria. So here in the y-axis, you have the date. You have from 1 June to end of August. And here you have the 32 model of semi-6. So what we can see here is that here you have the mean ensemble of the model, and here you have the date for era 5 and the start of the season for SHIRP. So you can see that SHIRP, the rainy season is more early in SHIRP compared to the model or to era 5. And this could lead to big difference when we can see around the impact on crop yield. We can see that for the model, we can have more impact than if we use SHIRP data. Okay, so here we present you the bias corrected that we performed during this study. And yeah, so here it is just a paper, a figure from Seoul, one colleague in the lab, who show this dipole between the Sahel, Central or East Central Sahel and Western Sahel. And we can show that here we will experience a decrease of rainfall, and here we will have more rainfall. Okay, here we use, here it is a ensemble mean of the model. So here we don't correct the model. We have the model at the original format. Here we make an CDF bias correction, and here we use random forest to correct it, the bias in the model. Okay, so after here we show you the precipitation, temperature, the temperature maximal, minimum temperature, and here you have it is the same precipitation, temperature, maximum temperature, minimum temperature, and here you can see before the correction, before the bias correction, it is in red. After the bias correction is in green. So we can see that the correction can improve the peak of the rainfall during the season. And here you can see that some limitation about the bias correction, because if you take a look, the extreme events is not good even in the after the bias correction. Okay, so here you have the temperature after the correction and precipitation after, and what we see is, and you have here the near feature, the mean feature and the far feature, like this one. For the temperature, it is, you see here you have the significativity of the difference, and you can see for the temperature we have a good agreement about the model, but in the precipitation the model is not agree very well about the evolution of the rainfall. So here, but you can see here that in the near future we will experience more rainfall, but in the mean and far future we can have more drought in Senegal. Okay, and if we see this result is about the temperature, what we can see is always we have the three scenario of climate change. So you have the SSP 126, SSP 245, SSP 585, and here you have the near future and the far future. And we can see that for the near future, we have not the effect of scenario of climate change scenario. So we will have an increase of 1 degree Celsius in Senegal. But if you go to the far future, we will see that in the most pessimistic scenario, we can reach 5 degrees Celsius of warming. And for the temperature minimal and the temperature, it is the same. You can see that. So if you want to see the impact of climate change in the semi-fixed data in Senegal, you can go to the far future to better see the impact, the fingerprint of the climate change. And here it is about the extreme events. So here you have all the extreme events which we computed. You have here the rainfall, the length of the rainy season, the end of the rainy season, agronomic end, and the onset, agronomic onset. So the result is very clear. Again, let's slide. No, no. Okay. So here the result is very clear. So we will have, you see that the dry spell is here. The dry extreme events will increase in the climate change, in the warming climate, and the wet season, you can see that here, will increase, but in the near future, in the black box, you can see that here. So in the far future, we will have just an increase of the dry spell, but not in the wet spell. Okay, so it is just to show you that this work is in collaboration between many institutions in Senegal and the research institution like the University of Dakar, the University of Ziguinchor. And we use also, how do you say, the national framework led by ANASIM to give some data from ANASIM and from another institution like Israel, like DPCC, like the Food Institution, to make all this work. And it was very interesting. And for me, I was designated to make the work for the agriculture sector. And the next slide is, okay. And what I do, I just take three, what we can call it impact model. So you have desert, you have WOFOS, you have SARAGE, and here you have an conceptualization of the crop modeling. So you have five box. Here you have the wizard, where you have to put your wizard data. You have the management from, for example, when the farmers will start its season, when they put fertilizer, when they put irrigation. And here you have the soil atmosphere interaction, the soil, the type of soil that you have, and the phenology of the plant. Okay, so here you have the result from the crop model. And for this panel, you have a peanut, and for this panel, you have yield, you have millet. And what we can see is that we will have a decrease of the crop yield in the future. And for desert, because here you have WOFOS, and Sahara model, and here you have desert model. But in desert, this decrease is not very significant. So in Sahara, you will have a decrease. The most we can consider Sahara as the most pessimist crop model. I'm finished.
So thank you, Chef, for your overview talk about monsoon and its societal impact. I think now we are a little bit behind the schedule. So the option is, I mean, either we go right away on the discussion panel and just use this opportunity, and then we can go lunch maybe a little bit later. Now, Chef, you're not here. Where are you going? So for the panel discussion, we have Professor Maria Molina. You are including, sorry. And then Jonathan, I don't know if Jonathan, are you online? Maybe not.
Yeah, I'm here.
Yeah, cool. Yeah. And then we have Cedric and then Cheikh. So we have two main points. The first one is about the current challenges in predicting the African monsoon. And then the second point is about record-breaking weather extremes. I think this is related to extreme events in recent climate causes, impacts, and so on, and about also the sub-seasonal, sub-daily to S2S predictability. This goes to Marisol talk. Yeah. So the floor is yours. I think maybe people has already questions for Cheikh. I did have one for Cedric. I think at some point you show the different ENSO impact on the extreme event. But the 2016, it was quite curious actually for me because it was one of the third biggest El Nino on 2015, 2016. But what is the other drivers that kind of hide the effect, make the effect a little bit smaller compared to the 1998?
Yeah, that is, you are already, you are right, because the 2016 event, El Nino event, was very strong, and its impact was actually been affected more region around the world. And I think that for this case, we can also have some interconnection driver, and also some hits coming from the continental part of some processes in the continental part of the region, because this is actually what I'm looking for actually right now, but I don't have actually a resources to investigate which are actually those phenomena which control actually which reduce actually the influence of the 2016 El Nino event on the heat wave occurring in the Guinean region actually.
Okay, thank you. I was, yeah, maybe I'll let people first. We can talk later. There are a couple who would like to talk. Okay, go ahead.
Thanks.
Present yourself.
Okay, my name is Yamogo Isaac from the National Med Agency of Burkina Faso. I have a question for the Dr. Cedric. First, thanks for this work, and I think it is very important for the Met Agency, for example, because the increasing of heat wave, it is important to develop some project, some weather information about this. So my question is about this. Your work, it is we develop some tools we can help people like me, like a meteorologist, or like people of Met Agency to use your work, your result in order to improve your weather forecast and another. It is my question for you. Thanks. And after I have a question for Dr. Cheikh. The first question is about the dipole of the dipole in the future rainfall in the Sahel. Do you investigate about the physics or the explanation of this dipole? It is the first. The second question is, if I see your presentation in very, we have I think the variability of the result or different, or this different model, or we have more variability in the model, in the impact. So my question is about the communication. How do you communicate for the politics or for the people to take action about in terms of variability? Thanks.
Yeah, Cedric, can you comment on that and then share? And then we have other question also for you guys online.
Yeah.
Tata.
Okay. Yeah, that is very interesting as a question, because at this step, the work that I present was actually carried on during the NR steward, which aimed to develop a early warning alert system. But at this step right now, we are most focused on the scientific aspect. So we try to make some analysis to develop some indicators. If you see, you remember in this presentation, I showed different indicators and how actually different type of heat wave can actually impact the population. So the idea will be to aggregate this information in one tool, and also put inside the information about the dry spell that have been presented by Cheikh, about air pollution quality, air quality, and make them actually available in one tool that can be actually used to help meteo service in the region, or also population to have an idea about what is actually going on tomorrow or the next week, to have information actually about the current weather situation concerning extreme event.
Sure. Can you comment?
Try to, yeah, for your question, I think, yes, for Isaac. Okay, I think that for the mechanism behind this Sahelian dipole between the central and the east Sahel, between the western and the east Sahel, so it is not clear for this moment. So because sometimes people related to the Mediterranean change and more flux humidity from the Mediterranean. Sometimes people talk about the declination of the ITCZ because we will have a ITCZ more in the north in this area of Central Sahel. So it is not clear, but it is a challenge because I titled it challenge, scientific challenge, because it is not clear for this moment. But we have to take into account about this spatial variability in the future in our project, because there are microclimate risk. I think microclimate risk have two hubs, one in the east, in the east Sahel. Another, we are trying to have another in West Sahel with Prof. Amadou, and maybe we can try to give some, to do some work about that, to try to explain this mechanism. So for your uncertainties on the CEMIC model, yeah, impact model, yeah, it is a big question. I don't know how to reply to this question, but yeah, it is very difficult. Sometimes we are not in the same square between the researchers and the decision makers or in the end users. But I don't know how.
Just for that, there was a very nice talk from Ted Shepard during the OS and her student. It's all about uncertainty communication. So the input data are already uncertain, and you are putting in the impact model and trying to draw conclusions. Then you have really to take into account on the uncertainties about the models, how you propagate this uncertainty into your impact model.
Okay, my question is for Cedric. Cedric, it's Mori Touré from Med Service Senegal. I have two quick questions for you. Are you using only temperature anomaly as explained in prediction, or have you considered integrating additional input? As Prof. Maria mentioned that ML is highly data drive. Because I just see temperature anomaly for your ML approach. The first question is, why did you test the model using training period data? Is there a risk that the model might overlap or perform a useful will or on the data it has already seen? But if the data, if your model are already seen the same model, the same data, I think my opinion is not the very wide use. Okay, thank you.
So can you comment on that?
Yeah, of course. Okay, Maury, thanks for the question. For the first question about the input of the machine learning algorithm, the idea behind it was to make a bias correction, and for this analysis or for this work, we for the first time focus on anomaly of temperature, and I agree with you that we can add another different predictors of humidity, of geopotential, of wind speed. We can add another feature, but at this step we will want to actually explore what is going on by using only the anomaly of temperature, but we can have more accuracy in the classification, maybe by add another feature or predictor. And for the second question, you tell that about the training set. Is that, if I remember? The second question was about the training set and the test set. If it is, if I am right, Maury?
No, wait.
For the trend period, for the trend period, I think I see 2000 to I don't know the another date.
16 years. Yeah, it was 16 years. We took
Yes, and the
16
test
years.
period I see 2003 to I think the another date. But your test period is in your trend period. Yeah.
Not yet, because the test year, yes, I am getting your question. We have actually 20 years, and we remove 4 years for the test. So we have 16 years for the transit, and the 4 years for the we have 16 years for the transit and 4 years for the test set, and the 4 years are not part of the 16 years.
Okay. Okay, thank you, Cedric, for your presentation. I have a question for you. For your evaluation of the stress model, I see, I don't know, we use the control member or the ensemble member. But if you use, for example, the ensemble member, we know, for example, for S2S model, the model do not have the some initialization date, and now the some number of member. Voilà. But I don't know what do you use for your comparison, because if you use, for example, sometime what approach, well, I don't know, I like to know what approach do you use to compare them without to favorize any model.
Yeah, that is actually a good question.
Okay.
Yeah, that is actually a good question. So for the comparison, what we done, as you said, you have different initialization time when we deal with sub-seasonal forecast model, and actually the number of member is not the same for all the model. And what we have done in this study is that we have transformed the probabilistic forecast in a deterministic forecast by fix a threshold. So when we take, for example, the SMWF model, we have in this case I think it's 25 member, and we try to say to pass from the probabilistic information forecast to the deterministic one, we fix a threshold. We can say that SMWF is actually detecting a hot day if at least 20% or 30% of its member is actually forecast correctly the event. So using this type of
Excuse me, I think you are not understanding my question, because I speak, for example, for use the data, we saw the initialization of SMWF, and you forcing this, we forcing them for ICMO, or we use a ICMO initialization, because there is not initialization. For example, ICMO, we see for one more, we can see 4 initialization. For SMWF in general is from every Monday and
Thursday.
Thursday, yeah, but it's different. Yeah.
Yeah. Okay. I get now your question. Yeah, I didn't. Yeah, that is right. We don't have the same initialization date. So for this study, I didn't take the same initialization date. I just take one initialization per week. I just take one initialization per week, one initialization date. I didn't take. We don't have the same date, so we cannot compare. But I take one initialization for each model per week. I don't know if actually is.
I think he's not convinced yet, but
yeah, we can. Yeah, you can exchange by in the chat or by email.
Okay, thank you, both presenters. My question goes to Cheikh. Which model, which crop you used to model? So you didn't mention the crop type. The other question is, as compared with other Saharan region, the Senegal is more affected by climate change. So do you have any argument for that? I need some explanation if you have. Thank you.
There are two questions.
Okay.
Why Senegal is affected by by climate change, and which crop model are you using?
Yeah, we use two crop model. We use three. Which crop? We use two crop. We use peanut and millet. And why Senegal is more, because we attribute we relate this high vulnerability by the Sahelian people, I think, because in Senegal you will have less rain. You will experience more drought in the future. Maybe that is but we don't have I don't have a reference to tell you that scientifically that is that, but yes.
What is the Atlantic decadal oscillation role on that? Someone else want to talk? Yeah. I think this also, may play a role.
Okay, thank you. My question goes to Cedric. During your presentation, you talked about dry heat waves and wet heat waves. So I would like you to buttress more about the dry heat waves with regards to which of the two is more predictable, and do they have the same dynamics driving them within the West African region? That is my question. Thank you.
Okay, nice. That is actually a good one. So dry heat wave and wet heat wave is actually defined by the indicator that we use to detect them. So dry heat waves is mostly associated to the 2-meter temperature, and wet heat wave will be associated to a combination of wind speed, relative humidity, and 2-meter temperature. And from a predictability aspect, from the predictability aspect, wet heat wave will be more difficult to predict because they account for many different climate variables compared to the dry heat waves. And for the dynamics, the wet heat wave are actually influenced by mainly fresh air coming from the ocean, and the dry heat wave is mostly driven by hot condition over the continent.
Any further questions? Jonathan, do you have any comments?
Well, I was really interested and excited by this idea of using machine learning to disentangle the decadal variability from the interannual variability signals in the Pacific. I'm wondering if that might also be helpful in evaluating the Atlantic multidecadal variability signal and what impacts we might expect that to have in West African climate change. So, it's sort of a question and sort of not, but Maria, if you have any thoughts about that.
So there is Maria who would like to say something.
You have one, you don't want a second one?
No. Hey, Jonathan, thanks for that question. Yeah, we're really excited about the idea to disentangle modes of climate variability that vary on different timescales in a more flexible way. And that was the motivation behind that knowledge-guided autoencoder and the custom loss function. And I will say, I guess, we ended up using a ERA 5, which was enough. We had to do some creative splitting of our training and test data to be able to make it enough. Can you, the audio from your phone is just, sorry, it's an echo with the phone. So yeah, so we had to, we use reanalysis data, so we had to only focus on the longest time scale being decadal. Does that make sense? Like we couldn't do multi-decadal. If we wanted to do multi-decadal, we would probably have to switch over to a perfect model framework, or use something like a pre-industrial run, something that has centuries. Otherwise, we don't have enough different AMOs or Atlantic AMVs to be able to characterize something varying on such a long time scale. And so that's my comment there. But you can use the knowledge guided autoencoder to evaluate climate models. So we actually trained with ERA 5 and then froze the KGAE, that's what we're calling this knowledge guided autoencoder, and applied it to CESM and E3SM, the DOE model. And we're able to characterize both modes of climate variability using that pre-trained model. I will also quickly add that that it also identified a quasi-biennial oscillation within the tropical Pacific. And you can also use it in a residual manner to remove the modes of climate variability that the knowledge-guided autoencoder finds, and then continue iterating recursively through the same model to continue extracting other modes that perhaps provide less variance explained. Sorry for a long answer. I hope that helped. I'm happy to talk offline too.
No, that helps. You actually answered a question that I didn't ask as well, which is whether you've been applying this to climate models. We've been actually playing around with some physics-oriented measures of decadal variability. It'd be great to compare notes. But also mention there's a question online, it looks like.
Okay, hi, Jonathan. Now that you are here, because yesterday I had a question about the reanalysis intercomparison project, but when I checked time, I noticed it was close to midnight in Beijing where you were. So yeah, so the point really is the intercomparison, because I've done for the ocean like heat budget, like using multiple reanalysis for specific a small region like the Atlantic and region. So, and in the end, what you really get is like a kind of a spread for the different terms that are supposed to be driving the mixed layer heat budget, for example. And when we evaluate models, we can always compare with observations or reanalysis as a kind of a reference. So in the end, what you end up with is like, okay, in different reanalysis, different processes drive or dump the process, and okay, there's a very wide spread. But what is this is not satisfying, because in the end it's hard to say, okay, so what do we compare this to? Because these are observations, and so I just wanted to know like your thoughts on what you guys are doing. Because I find that quite interesting, because like for the West Africa monsoon region, for example, there's really very big problem with the reanalysis, and unfortunately there's really nothing else to use, in terms of the field variables and all that.
Yeah, so currently we're trying out a few different ideas. Now, I agree, there's no good benchmark. And so we can really only evaluate the reanalyses against each other. So seeing to what extent the contributions within the budget are different between different reanalyses, I think can be instructive, but I agree, it's not satisfying. So some of the things that we're working on are trying to break the budget down in some different ways. And so what I've been preparing for the exercises for this afternoon is focused on a kind of vertically integrated budget, so that we can observe components of the budget that we can then tie back to the unobservable parts. And we've also been playing around with Lagrangian models, so linking our detailed breakdown of the budgets to Lagrangian source attribution and evaluating that against idealized models like the water SIP kind of framework, where you're trying to identify moisture and heat sources and so on. And so by pitting the reanalyses against these idealized conceptual models of what processes we think should be important, we can start to see where the differences are coming from and how those differences might be closed, or at least the uncertainties could be narrowed. I'm not sure if that fully answers your question. I don't think there is a full answer to this question at the moment, but it's something that we're actively working on, and I'd love to have further discussions with anybody who's interested.
You have another question here. We have another question here in the room.
Hello, my question is just to clarify with Cedric. Can you confirm that the baseline for your studies is the 1993-2020 for all the anomalies you get in this study, or it is the same baseline?
No, it's not the same. For the monitoring
Because in
study,
your presentation, I did not see anything related to that. So that's why I'm asking just to clarify. Yeah.
yeah. For clarification, for the monitoring study, is the baseline is 1993 to 2020. But for the predictability one is 2021 to 2020.
Okay, and another question for Maria. I would like to ask, because I am working with the same score, the dichotomous score that Cedric present here in his work, like the GSS. There's other scores we use for predictability and for focus. And I'm asking if it is relevant or it's not outdated from the use of AI to combine like those information we can get through this dichotomous score of focus, and to improve the score of predictability of heat events, for example. Yeah, it's a metric like the false alarm, the hit, and the correct prevision, like the yes and no forecast. Like you combine the observation with the model forecast, and you try to get to compare the results. Like if the events you select is well predicted by the model, if you compare that with the observation data. So there is a list of scores, we call it dichotomous scores. And I see that one of them, Cedric present one of them, the GSS scores. Like, you don't know about that?
Prediction moment. I think it's about metrics to kind of compare the models, to validate the models compared to observation.
Yeah, I guess. So you're asking about multi-class. Yeah, this is a confusion matrix. So it's a classification, like if it's a hit, yes or no. Yeah, so you're asking if we can incorporate that into like a loss function for a model?
Yeah.
Yeah, so so those are a little bit more complicated. So for instance, if you're trying to assess critical success index, or let's say hit rate, there's a number of things you can derive from the confusion matrix. Those get a little more complicated because the model predicts in probability space. So it gives you like 0.5 this class, 0.5 that class or something. You have to pick a threshold to convert it to which class is the one that was predicted. Does that make sense? Like even if, let's say I'm using a neural network and I'm predicting, I have it in a classification problem for its yes, no, it'll give me a probability for yes. So let's say it might say 0.7 yes. That means kind of like 70% yes. And so I might interpret that way and then assign that as the yes class. So let's say that my hit. And then I can convert that into the loss function, but it is a little bit more complicated because there's a subsequent step. But you can. Yeah, and then there's other ways to, let's say if you have class imbalance under that scenario, you can either increase the weights for the minority class or other such approaches. But those concern any such metric derived from a confusion matrix, you can incorporate it into yeah.
So if we identify like one pattern from all the hit events we detect in our like database, so we detect one pattern like a regime as you define in your presentation. If can we base like our analysis and combine like those patterns in order to improve the predictability of the model? So it will be like not a direct focus, but indirect like focus based on the pattern we yeah. Yeah.
So as I understand it, it's kind of like you're asking about conditioning. So like, if this is the regime, then like tell the model this regime is there, and hopefully it can do better knowing that it's that regime.
I detect in my research, I detect one kind of pattern related to, you understand it?
Yeah, for sure. You can do conditioning based on weather regime. Yeah, I have an example tomorrow where we not only can do conditioning to improve predictability. So we're telling the model that's, for instance, that's the lead time. We're 2 weeks ahead instead of 1 week, and having all that lead time in one model. But that also enables us to increase the sample size by being able to it's the audio, to be able to leverage all the data that we have available. So if we, instead of training a bunch of little models for individual regimes, you like bake that all in and you condition based on regime. Yeah, we can talk more, but yeah, you can do that.
Any further comments, questions, or whatever? It is online, some stuff online. So if there is someone online, just please unmute yourself. And probably this is the last question we will have before lunch. I think there is couple questions of online people. Yeah. Okay, maybe we get a final one from the here in person, and then we can go for lunch. I think everybody is hungry now.
The second part of the panel discussion, we can say something about this.
Go ahead.
Just no, for about the, because for me, I don't have the. Okay. Oh, it is the question because I don't. It is really
a little bit about this. How the
if the different panelists we can say something about it.
Yeah. So there is a request of comments about the regional climate. I mean, mode of variability impacts on, on the record-breaking heat wave. I think this is a part of the static presentation and so on. Do you have any further comments or message that you would like to share with the in-person and online people? I'm talking to the panelists. Yeah, like Cedric, Cheikh, Jonathan, Maria. Do you have any further comments? Yeah. Cedric? No? I think he went for lunch already. So, Jonathan, do you have any last comments? No?
Sorry, trying to use the mouse. No, I don't have any further comments at the moment. I'll put some things in the chat on questions that are here, but nothing has been raised specifically. Thanks.
Hi, Jonathan, can I ask you a question? No.
Yeah, sure.
So I wanted to know about this. Is this going to be like the MIPS we have? I mean, what would be the output? Will you have like data that will be kind of publicly available at the end of it? I mean, I'm really interested in knowing where this leads to and maybe getting involved at some point.
Yeah, so we have several data sets that we're working on. There's one that's already public, and this has lots of reanalysis, but it has a limited number and sampling of the variables. So it's mostly zonal mean fields, and it's mostly focused on dynamics. We're also working on some data sets that would then be more fully resolved and on finer grids that would focus on the most recent reanalysis products. And those are in process, and we hope to have them published sometime, maybe towards the beginning of next year. In the meantime, it's possible if you get in touch with me, I'd be happy to share some of the data if you'd be interested in looking at it, or to give some information. I think my slides are in the Google Drive. I think I put them there. So you can take a look. There's information about what we've been working on there. The last thing I would say, we are working now more on these composition and chemistry reanalysis products. And so things related to air quality, we're hoping to produce some intercomparison, common grid, similar types of diagnostics for those. But that's at a much earlier stage.
Okay, thank you very much, everyone.
Yeah.
So let's thanks the speakers of the morning sessions and Jonathan, I say good night. Not yet.
Not yet. I have more responsibilities, right?
Yes. So
see you after lunch.
Yeah, see you later. We are going to have a lunch and then this is the hand-on session. After that, we have Jonathan and then Redwan. Okay, so I think you have already received the emails and the links and so on. Yeah, so let's go have lunch and we will get back here around 2:45 UTC. So yeah, and we are on time today, so that's good. Thank you everyone. And one information, guys, don't forget to bring back your plates on right place, right? After lunch. Hey.
Not the other one. Oh, okay. So that's supposed to be the other one. Yeah. Okay. Thank you. Okay. Yeah.
Ça va? Oui. Il y a une personne qui doit présenter la demande le lien. C'est bon? En fait, ça si tu veux lui faire la demande, on va essayer de parce qu'il y a trop de personnes qui vont tout le monde, mais ceux qui font une petite demande, on va évaluer. S'il y a un nombre raisonnable, il n'y a pas de souci. Mais s'il y a beaucoup, tout le monde qui veut, donc ça va. Il suit. Il est sur le petit WhatsApp. Essaye de l'écrire dans le WhatsApp. D'accord. Oui. Oui, au remboursement, on disait en fait, est-ce que c'est possible
About the vous êtes dans ce cas-là ou pas? Vous êtes capable d'en avoir? C'est pas encore lui. Mais il y a possibilité de l'avoir ou pas?
Comme c'est déjà passé, c'est bien de savoir
Vous êtes dans un laboratoire. Oui, oui, mais est-ce qu'il n'y a pas moyen de le faire? C'est juste dire, bon, c'est une lettre formelle en fait. Avec
vous aviez envoyé un
un
exemple.
template, ouais. Ouais, vous pouvez le faire, mais si vous avez une signature, donc c'est bon. C'est avoir une signature officielle. Après, c'est bon. Ça, c'est indépendant. C'est juste ça. La signature officielle, peut-être je vais en parler. La signature officielle de votre responsable. Ouais, comme il y a un numéro de, il y a, comment dire, il y a une référence en fait. Professeur tel, ou directeur tel, il y a son coordonnées. D'accord, merci. So let's go for lunch.
Can you hear us? No?
Yeah, can you hear me?
Yes, yeah. Can you hear us, online people?
Yes.
Okay, thank you.
Yeah, that's nice.
So I think his time is on now. So we are going to start the afternoon session. So the how we can say we have hands-on sessions over the whole afternoon. The first one of them we will start with Jonathan. He has already presented his hands-on session on Monday, just to share and show what just the program quickly. Yeah, on Monday he have talked about his hands-on session that will be about African monsoon onset and dynamic. The hands-on materials are already available, I think, on the GitHub and also on the Google Drive. We have already circulated it by email. So yeah, I think Jonathan, you can just start. You want to share your screen and maybe explain them how to what to do. So the floor is yours. I can stop sharing. Are you online, Jonathan? Yeah.
Yeah, I'm here. I'm here. So I think there's maybe a little bit of confusion about exactly what I had in mind for these exercises. So what I put in the GitHub and also on the Google Drive, and which you can access then from the link in the chat, is a set of notebooks which are focused on getting started with climate data analysis. And there are some examples focused on atmospheric composition and air quality, precipitation, and temperature are the three that I looked at. There's nothing in here that's specific to the onset of the West African monsoon, but I did put together some exercises, which I can send later on. But I think let's see how we get on with these 5 getting started examples. Right? So basically just trying to demonstrate some of the tools that I use on a pretty much a daily basis in my work. Right? The first notebook here, which you can click through and run in Google Colab if you want, is for if you have almost no experience with Python at all. Right? So you kind of know what Python is, but you don't use it on a regular basis, or you don't have much experience with it. And so it goes through some of the basic building blocks. If you are very familiar with Python, you can go ahead and open the second module and you can start taking a look at that. All right, so in this first one, I go through a little bit about how Python modules work. You know, that you can bring in different aspects of the program that allow you to do different things, as Maria mentioned in the morning, and also how you can build your own environments if you want to do that on your own computer as opposed to in a Google Colab. So in Google Colab, once you open that, you can click to run each section in the notebook. Have you done Google Colab up to now? Was that a part of the exercises yesterday, or is this new today? Moha? Did you use the Colab yesterday? Not, I think, right?
Can you repeat? I didn't hear well.
Okay. Have you worked with Colab yet this week?
Yes. No, this week,
okay.
No.
Okay, not this week. So you have, but the group collectively may not have. All right, so.
But apparently they all.
They all are familiar with this. All right. So then I don't need to explain some details of this.
Jonathan,
Yep.
I think your mic is kind of too loud, maybe,
Too loud.
or too much
Okay.
echo. It's a little bit hard to hear
Let me
well.
Okay, let me check. Which one is it using?
It looks like the mic is too close.
It's on the headphones, so I can't really make it any closer or farther away.
Okay, then it's maybe an echo issue.
So I just changed the setting. I don't know if that helped at all.
Wait, is it possible to... C'est possible de gérer... Parce que quand il parle, il y a un écho.
Un écho.
Mais je pense que ça vient de lui. Peut-être qu'il n'y a pas moyen de diminuer un peu le volume pour voir si...
It says it was automatically. Yep. You want the volume up or down?
We are trying to reduce the volume here just to see if it can get better.
Now I can change the volume on the microphone as well. Is that any better?
Now it's better, I think.
It's better? All right.
Can you increase your screen? Sound really? Okay, so you're good to go.
All right. So there, the modules that you'll see in these examples are the same ones that I am typically using in my research and also typically using in my classes. And the most important module here, the most important modules I would say are these two, NumPy and Xarray. Is anyone
Jonathan?
Still not okay? All right.
Jonathan?
Yep.
That's echo, but sound is
Tu penses au niveau de la salle?
Let me try something.
I think, can you maybe reduce a little bit your volume?
Reduce
if it's possible.
again?
Yeah, a little bit.
All right, hold on. Let me stop this for a moment.
Ouais. Pourtant, il utilisait ça depuis. Ouais. Non, pas trop, je pense pas. Redouane? Redouane?
Oui, je suis là. Moi, j'arrive en fait à entendre Jonathan, hein. J'arrive à l'entendre. Je ne sais pas pour les autres qui sont aussi en ligne.
Non, parce qu'en fait, ton son là, il est propre ici.
Ok.
Quand
Ah,
tu
d'accord.
parles,
Donc, il y a une différence. Ok.
Il y a un écho.
D'accord.
Donc, le son est propre. Donc, c'est sur lui l'écho, ça a été différent, en fait.
So is this any better? Hello?
Yes.
Can you hear me any better now?
You have access to the Google Docs, right? Yes. Can you copy the collab or the email that I sent yesterday? Can you copy the the documents here on the chart.
This document.
The hands-on exercise.
How's the sound now?
Augmenter le volume un peu. Yeah.
Which one do you want me to?
The hands-on for static for.
Let's go down.
No, not this one. Jonathan, Sekri Jonathan. Who
I
uploaded?
cannot find it.
Jonathan, yes. Can you speak a little bit louder?
Yeah, well, I mean, I can also turn the volume up.
No, now it's fine, I think. Now it's
Now
fine.
it's fine. Okay,
Yes.
I switched computers. I'm
Partage.
logged in on a different machine now. So
Soit vous copiez le lien directement. You can copy just the link to the chat.
Okay.
So yeah, have you all access to the Google Colab? Yeah? You have access all to the Google Colab? All of you? Okay, so you can start now. I think they are all on the same page. For
All right.
online people, we are copying the email that Jonathan sent, that you can also access to the Google
well, I
Colab.
think it should be in the chat already. You can just reply or copy it back into the chat.
Yep.
So in case people have logged in since.
Yeah.
So that will take you to this page here.
Yes, it is there. Yeah. Okay.
Yeah. So you can run this on your own later on, or you can use the Colab as we work through them. So the way that I've organized these, everything is built around Xarray, and Xarray is sort of a do everything program. So this module can sit at the heart of pretty much any climate data analysis that I want to do, right? So I can read in files. We'll see an example of that just below. I can use other modules that are built on Xarray to do various kinds of calculations. I can do lots of, I can chop and reorganize the data in many different ways. It's very useful and powerful program, right? So that's what I am typically working with. If some of you may be more familiar with Iris or something like this, there are other options, but I built these around Xarray for convenience. Right? So for mapping, we'll typically use this module Cartopy, which is more frequently updated than other options in recent years. And then there are various statistical tools that we can use as well, like so. Right? So these are just examples of what you might expect to see. For Colab, I've put all of the data files you need in Google Drive, and you can access them like so. It'll pull the data file into the cache. And once that's done, you can go ahead and read it in, right? So for netCDF files, this is very easy to work with Xarray. You just need to make sure that it has the right backends, the netCDF4 module to work with. You can also do this with, yep, can you hear me? Yep.
Yeah, just, is it too fast on the room or it's fine? Is it too fast for you guys? Yeah. Or it's fine?
I'm sorry, I can't see the room.
Okay.
This is a little.
Okay, it's fine.
So
it's fine.
yeah.
It's fine. Okay.
Right.
You can go ahead.
So you're very welcome to stop and ask questions at any point. All right. So once we read in the file, we can take a look at what's in there. And in this case, this is 3 atmospheric composition variables: aerosol optical depth, the total column carbon monoxide, and the total column ozone, right? From the CAMS reanalysis. And this is the largest file that I've included for you. The rest of them are quite a bit smaller, but it's monthly means, it's a global field, and you can see some information about how this has been prepared. You can see where it comes from and various other aspects of this. So let's say we want to take a look at the aerosol optical depth. And so this is just an object, right? So it's indexed like you would in a dictionary with the name of the variable in a string. You call that from the netcdf file, and then you can see the various attributes associated with that. So it's total aerosol optical depth at 550 nanometers. And if you want to kind of go back and look at where it came from, you can get this kind of information as well. Right? And then if we want to take a quick look and see, maybe we don't know what the range of aerosol optical depths is, but we want to make a nicer plot later on, then we can just make a quick look plot, see what is the automatic color bar, what does that look like? Can we see this distribution? Here we can see the outlines of the continents. We can see where the aerosol optical depth is somewhat larger or smaller within the global distribution, right? And so throughout these notebooks, I've also included some links to more information, more detailed tutorials. And so if you don't have experience with X-ray, you can take your time to click through these and to take a look at how you can use these objects to work with various data files. And X-ray is really nice for climate data, but it can be used for many other kinds of data as well. I'll show you an example for a CSV file a little bit later on. You can also use with ZR files. I'm not actually sure how to pronounce that one. GRIB files with meteorological data, and there are other file formats that can be used as well, right? Are there any questions about these basics? Anything that you want me to kind of slow down and go over in a little bit more detail? Or is everybody familiar with Python and happy to get stuck into the more interesting stuff?
Is there any problem, any question? Okay, so it seems everyone is going along with you, Jonathan.
All right.
Oh yeah, so there's a question.
Okay.
Yeah, can you explain more the type of data set NC, the file that NC, please?
Yeah, so NC is, I think netcdf is almost exclusively used in climate data analysis. It's the standard format that most of the climate data centers will default to, and it has good relationships with, let's say, interrelationships with other file formats that are also used for climate data. I don't know a lot about the details, how exactly it works. But what's nice about netcdf is that it's relatively intuitive to work with. So once you read in a netcdf file, you can get a lot of information directly. And that information is available through a number of different ways. There are external programs that you can use to read netcdf files, read them in and plot quick look plots. There are command line tools that you can use to see what's in the file. And with netcdf, everything is in a relatively user-friendly format. Right? So with some other file formats, you have to really dig into the organization of the files, and maybe in groups, and it's not clear how these groups are organized, or with a grid file, it may not have the appropriate information on the variable names attached. And so tracking down which variable corresponds to what field can be very difficult. So I would say NetCDF is the most common format that we work with, and that's because it's relatively easy to work with. A lot of people are using it, and there are many tools that have been developed to work with these files. If anybody knows more information about the details or wants more information about the details, you can chime in.
Okay, is there any further question or we should proceed? Okay.
All right. So now we can get into a little bit more of plotting spatial distributions and how we can make those look nicer than that very quick plot, right? So again, we'll need to load the modules to start. That will take a moment. And then we load the data file. It's the same file as we used in the previous notebook. And then let's say that we want to actually plot this distribution of the aerosol optical depth for a presentation or something to illustrate the distribution of aerosols globally. Right? So to do this, we use the CartoPy module that I mentioned before. So here there is a link to the landing page for the module that will have all the information from the very basics, getting started, to more details about how the module is organized, the different things that you can do. But this link will take you directly to the getting started, right? So if you haven't used CartoPy before and you find it extremely confusing, or if you run into problems, you can look for answers there. And we're also using the core Python data structures, which I will assume you can click through and learn more about later on. Right, so let's say we want to plot a distribution globally. What we have here, we first create a figure. After we create the figure, we can create an axis, which this is an object that we will add the plot elements to. And then we can define various aspects of the plot. Once that shows up, you'll see how that looks, right? So this variable is defining the color bar. Right? So what's the label? Do we want it to be vertical or horizontal on the plot? And the tick labels and so on, right? And we've loaded a particular color table. There are many of these. There's links also included in the notebooks if you want to see all the different color tables that you can use. Here we are defining how large the range should be, and then giving some information about the plots. And so this says, I want to use these colors. I want to use these levels. I want to extend at the higher end, but not at the lower end, right? So this could be max or min or both or neither. And then I want to plot this on a map. So I can create a particular transform. This is what translates the data, which has a grid attached to it, latitude, longitude information, that translates that to the locations on the map. We want to add a color bar so that we can see what the values are for different colors. And then we'll use this information to clarify what's in the color bar and its range and so on, right? So All we have to do to plot is the same thing as we did before. We take the object, which again is coming from here. We've read from the netcdf file the variable named AOD550, which corresponds to aerosol optical depth. To take the time average for the whole period, we just say, take the mean over time, right? And so this is where Xarray really shines in these kinds of intuitive methods that you can apply to your data. And then you ask for a plot, and you say, I want to put it on this axis object that I've defined up here, and I want my plot to show up with these features. The next thing we can do is add the coastline. So for example, you can see what happens if we remake this plot and we don't add that variable. What we'll see then is the distribution, but without the coastlines. And so CartoPy is not the easiest module to work with. There are others that are somewhat easier, but it is, in my experience, the most flexible. Right? And so it has a lot of these shape files which are predefined, which you can load and add directly to your plot. You can also download shape files. So let's say you want to plot only within a particular country. You want to plot just the country. You don't have anything else is showing up on the plot. You can download a shape file, you can fill in, and you can cut it. CartoPy makes all of this not necessarily easy, but straightforward. And so it's flexible. Right? And so the most difficult thing with CartoPy, or the most likely problem that you will run into, is related to the transform keyword and the various ways that this shows up in your plots, right? So these are the most common errors. You can see some more information about this. One of the problems is that it's not always clear which one of these you should be using, projection or transform or CRS. And it depends on where the method that you want to use is located within the overall ecosystem. The other problem is that sometimes it's relative and sometimes it's absolute. And so if you plot something and you're expecting a global distribution, but you only see data to the west of the date line, then that indicates there's just an issue with the numbers. You need to figure out how to rearrange the information so that your plot will show up globally, right? And so let's say we want to do filled contours instead. The first thing we need to do is add a cyclic point, because otherwise this will show up with a white line in the middle. Then once we do that, we now define a different color map. This website has a ton of color maps, which are often very useful to make your plots a little bit prettier, a little bit easier to read. And basically we're doing the same thing. We're just using a different color bar and a different type of plot. So you can see the difference here is that in this case, I've used plot, and in this case is plot.contourf. We could also specify that we want this p-color mesh. It's not so easy to see here, but I'll show you an example later on about what the difference is between these two different kinds of plots. Right? We can also select a season and then average, right? So let's say we don't want the annual mean, we want the mean for September, October, November. Right? And now we want to plot the difference, or let's say we want all the seasonal means. Here we can, if we group by season and then take the average over time, then we'll end up with an object that instead of having 200 something months now has 4 seasons, and all of them are averaged over all the years that are in the data set. So you can access those now by DJF, JJA, MAM, SON, like you expect, right? And so let's say we want to take the difference between September to November minus March to May, and you can play around with this, choose different options, choose different color sets. and yeah, see all the different things that you can do within this, right? So we take a difference between a selection for the season SON and a selection for the season MAM. We then plot that, and we get this difference where we can see the AOD is larger during Northern Hemisphere spring in the Northern Hemisphere and smaller in the Southern Hemisphere. Okay? We can also zoom in on a particular region. This is where things can sometimes get a little bit complicated with Cartopy. In this case, we're choosing another color map, and we're zeroing in on the region where you all are right now, right? And I've also added a scatter point, a star here to mark the location of Dakar, right? And so in this case, because our grid is defined relative to 0, relative to the prime meridian as opposed to the date line, 180 degrees, we will set the extent according to what the actual longitude is. If it weren't, then we would have to play around with this to get things right. When you set the extent of the axis, you need to specify that you're using a geoaxis. Right? So you need to tell Cartopy that this information is on a latitude-longitude grid, right? And that's where the CRS keyword comes in. Then when you use the scatter plot, again, you need to tell it that this is longitude and this is latitude. And to do that, you use the transform keyword, right? As I mentioned, this is the part you're most likely to forget or most likely to run into problems with, right? And then the last one here, we can look at the change in AOD over a particular period. So let's say we want to look at September, October, November again. But then we want to see the difference between 2020 to 2024 and 2005 to 2009. And so again, you tell it to select where the season is equal to SON, and you want it to select where the years are between 2020 and 2024. So you can do this in two separate. Should actually have an I here, but it doesn't. It appears it doesn't matter. The difference between these two is that here you are indexing by what you would actually see in the dimension, in the coordinate, right? So you're indexing by 2020. If you use the I, then you're indexing by the location in the object, right? So the first or the second or the third, as opposed to the name of the variable, right? So here we have the difference between 2020 to 2024 minus 2005 to 2009. We can see that the AOD has increased, right? So again, there are lots of different ways that we can plot these. You can mess around, you can play around with different projections. You can go to this link. It will show you lots of options for how you can visualize your data on different kinds of maps. And let's see here, I can show you the difference between those two plot types. Here we had contours, filled contours, and the standard plot is like this. So it will actually show you the information on the grid that the data are defined upon, right? So I think I'll pause here for questions, or if you want to take a little bit of time to play around with these types of plots. And if you're ready to move on, you can also let me know. So. So I think here I'm really showing you how to visualize the data, but you would use a lot of the same tools and techniques to pre-process the data if you want to select, for particular times of year or particular periods or for specific variables. All of these, you can do this with the same approaches, right? So you can reduce the size of your data, you can narrow down on which variables you want. The same procedures apply, right? So here I think it's easiest to get a handle on that by plotting the distributions for different variables at different times, because you can kind of see what those differences are. But for pre-processing, for dealing with different kinds of data sets, the procedures are very much the same. Please let me know when you're ready to proceed.
I just wanted to check the time. Are you done? Okay. Yeah, I think it's done.
Jonathan,
Yes.
do you want to take any feedback from the room?
If there are questions or
I don't know. Do you have any
confusions,
feedback?
or if people want to keep working on this one before moving on, all of these are fine. You just let me know when there is a sort of a collective, a critical mass who wants to move to the next.
Jonathan,
Yes.
I have a question about the individual region plotting. So what explanation can you give about the height concentration of aerosol optical depth we have in the south? Because I can understand in the north, maybe we can assume that it's the Saharan desert. So in the south, I am not aware of this, of the existence of a source, a desert or a dust source in this site.
Yeah, so I think it's a good question. We'd need to look at at some additional variables if we want to determine it entirely. But just kind of looking at the magnitude of the point source here, I'm wondering if this is maybe a large fire, which then shows up, or a repeated area of biomass burning and a plume that's associated with that then shows up over the time mean for this season.
Yes, that's a good point. That was also my fault. Maybe the agricultural biomass burning, or which season is this? Is this
This is JJA.
Which?
JJ.
Oh, okay. It can be that actually. Any further feedback or?
There's a question online that you're welcome to unmute and ask.
Online. Oh yeah, sorry. You need coffee. No, you need coffee. No, I lost everything. What
Is Naja? Okay, there is a question online from Naja Gamudi. Hello, is it possible to separate the AOD natural sources from the AOD anthropogenical sources? That's for you, Jonathan.
Yeah, not with this data file, but theoretically, yes, by tagging the emissions. I can't remember whether CAMS offers anything like this. It gets complicated because you wouldn't be able to then apply the data assimilation, right? And so I do know that they have, for example, a stratospheric ozone, which is then not separately assimilated. It's a tracer that's used for identifying stratospheric sources of ozone in the troposphere. But I can't remember whether they have done something similar for aerosols. The other way that you can do this is by looking at the individual species, right? So just making a guess that dust is your primary natural source, and then the others you would say are so like black carbon, organic carbon, and sulfates are what's included in CAMS. In the more recent versions and in the new CAMS, which will be available, I think maybe starting sometime next year or the year after, there will be nitrates and ammonium as well, in addition to those. So it's not a very clear distinction, but it is theoretically possible. Yeah, and I think Ismaila has a question as well. There's a hand raised.
Okay, there is one online from Ismaila Ngom, I think. Can you unmute yourself? And then we go for coffee break. Ngom? Maybe. Okay, so if there is no other further questions, we can go just for coffee break and then come back for the next. Oh, it's a break, right?
I thought I had a
No. Sorry,
yeah.
I
I don't have the schedule open.
Yeah, it's break actually after Jonathan's session, and then
Yes.
back again.
Yeah, I mean, now we break normally after your session, but we still have a little bit of time.
Yeah. I think
say.
it should be midnight plus 15 minutes for me, I think. So 45 minutes left.
Yes, yeah. Maybe just stay online, and then have you tried what you have already shown on your own? Is it working? No problems? Okay. So it means then, Jonathan did very good his job. So maybe, I think. Do you have any other additional stuff you would like to share later? Jonathan?
I mean, I have more stuff here. It depends on how much people. I would say we might want to look at the next one at least.
Yes, we can do that. We are too early. Right.
All right. So if you go ahead and open the next notebook, we start in the same way and use the same file to start as well. The focus here is on time series. Yep.
Yeah, I have one question.
Yes.
Yeah, it's Damgay. And my question is, for example, I'm not common to use Colab, but sometimes I would like to use it if I am using a very big data or very weight data. So, for example, if this data is in my laptop, for example, can I just give it the path and just work with this data in Colab, not
So
in my.
I'm the wrong, yeah, I'm the wrong person to ask. Moha may know, but this is the first time I've used Colab. Being in China, I don't tend to use the Google stuff.
You can just upload it on Google Drive if you have enough space, and then you can use it.
If you have enough space, yeah.
Yeah.
But there should be some limit as to what can be loaded into the cache, right?
Yeah, I mean, he has to upload that in a Google Drive. You cannot connect it directly from the local computer to the Colab.
Right. Right. So yeah, I should mention this approach here is for files that have been shared, right? So I make this available to anyone with the link, and then you can load this without having it in your Google Drive. But if you want to use a larger file, you probably need to load that into your Google Drive, and then you just need to know how the paths work so that you can load it in a similar way. My understanding. Maybe someone else knows more.
So we can carry on. Maybe if there is not any further questions, he would like to show more like about time series, and then just the time we go to the coffee break. Jonathan?
Yeah, sure.
You're sleeping.
So
Too much Senegalese.
yeah. So we're using the same file, go through the same steps to load that, but now instead of the aerosol optical depth, we're looking at ozone and CO, right? So let's say you want a time series from a particular location. There are lots of ways that you can do this, but the easiest way here is just to identify your latitude and your longitude location and then use this method nearest. So then you don't actually have to know whether this is a point in a grid or not. If you don't use this, you have to actually select a specific grid point. You need to know what values are available within the dimension. But by using nearest, you can allow it just to pick whatever grid cell is closest. And maybe you want to do this in an interpolation way if you're doing something more sophisticated. Those options are available as well, but I don't include them in these notebooks. Right? So here we take the time series closest to Dakar, right? And in this case, because the longitude coordinate spans from 0 to 360 degrees, we need to specify the longitude in that range. And we'll see later on another example where it goes from minus 180 to 180. And then it would be just a minus 17.4. Right? And so we double check that this location that we've selected is what we expect. Right? So make sure it's close to where we actually specified. Right? And we can also do that by looking at the information attached to the variable. Right? So you can see here the longitude and you can see here the latitude for the point that has been selected. Right? And so now we have a time series, is monthly means again. And you can see how that's varying over time. Let's say that we want to look at the long-term changes in ozone and CO. Right? So one of the ways that we can do that is just take the annual average. Again, this is super easy in X-ray. So all you do is you say, I want to group by, year, because it's a netcdf file, because it has the time information. Right, so I'll show you here. We change this to O3. That's not, oh, right, because it's different keyboard. And you can see that the time index has the dates attached to it. And so anything that Python datetime or NumPy datetime can do with a date, you can do the same thing, right? So I have another example that I can share with you later on, not in this session, but just for exercises later on. You can select or group by the day of year, right? So that's something that used to cost me a whole lot of pain and time. But with Xarray, it's incredibly easy because all of this is then attached to the metadata in the file. If your file doesn't have this information, you can easily add it, right? So you start in the beginning and you say, I want time to be a series of dates that looks like this. I'll show you how that looks momentarily. Right, so in this case, we want to use the year. So we want to select the 12 months for every year and then average over those 12 months. And so we group by time.year and we take the average over time. And once we do that, then our object, and you can check this for yourself, now has, instead of a time dimension, it has a year dimension. And that year dimension is now a number ranging from 2003 to 2024. Right, so we want to select the year 2024. We would then write it like so. Select year equals 2024. And so now we have a single value. Then if we want to plot the time series for both species, since these have only a single dimension, they will show up as line plots. And we can see the ozone up here in the blue line and the CO down here in the orange line. These are the default colors. The first line you plot will be blue and the second line you plot will be orange, and then it cycles through. Right. And so we can set the y-axis, but the problem here is that we can't really see changes because the magnitudes of these are so different. There's a couple ways we can deal with it, but probably the best way is just to make another y-axis. That's what this does here, right? So we first create our axis, and then we say we want another axis that has the same x coordinate, right? And it shows up on the same axis with the same x-axis, but not the same y-axis. Now we plot the ozone on the original axis, axes, I should say. We plot the CO on the twinned axes. We now specify the colors that we want to use. We give labels, and we set labels on the y-axis as well. So ozone over here and CO over here. And so now we can see them both. They have different magnitudes, but we can see the variations around their average values for this period. Let's say we don't like the relatively coarse time resolution in this plot. We still want to look at the long-term time series, but we think that this plot isn't very nice to look at. So one of the ways we can do this is by using a grouping. So you can click through to this link if you want to know more about grouping, the various ways that you can do that. We've seen that a little bit already. But in this case, to take the anomaly from a mean annual cycle, we use two group by commands. The first, we would group by month, take the average over time. That gives us a mean annual cycle, right? So we can just show that explicitly. You can see that this has a coordinate month instead of time, and it has 12 elements. Right? So this is our mean annual cycle over this period. And then we subtract that from the grouped months, and that gives us the anomaly from the mean annual cycle. What is that? Oops, I haven't actually run that block yet. And now we have a monthly time series instead of an annual time series. And so it will show up in much finer time detail. We can do lots of other things. We can apply rolling functions. You can see that in the next notebook. I'll leave that for you to go through if the time is not enough. But we can make other types of plots as well. So I just want to show you a few of the things that we can do. In this case, we're using a different file. Now we're looking at surface air temperature from ERA 5. And again, we select the grid cell that's closest to Dakar. And now the latitude and longitude are slightly different, but similar to what we had before, just because the data sets are defined on different grids. If you want to see how those compare, you can just look at the metadata for these objects, like so. In this case, we open a file and we read out the variable in the same line, unlike in the previous example. And so we've done the same thing. We've grouped by year, and then we've subtracted the climatology. In this case, we're looking at a much longer time period. We decided that our climatology should be this period from 1961 to 1990. Right, so we've sliced here and we take the average over time, and that sets our baseline. And what does that look like? All right, this is basically showing us the warming signal locally over this time period as it appears in ERA 5. Now, to see a little bit more about what we can do, in this case, I want to sort by decade, and it's because of the specific type of plot that I want to make. So I want to sort by decade. First, I need to create a new coordinate which has the decade that each year belongs in, because this is not a standard aspect or attribute of the date time. Right? So I do that by starting from the beginning of the time period and using a relatively simple way of converting the year to the decade that it belongs to. Right? And then I create a new coordinate which contains that information and has the name decade, but is attached to the year or time axis. Okay? Let me run that. And then another module that I use very often is Seaborn. You can click through here. You can look at the gallery to see different types of plots. This is something that you will often use for statistical kinds of plots, distributions, histograms, and so on. Right? We can also do a regression automatically, which I've added to this plot. Right? So now we can see the temperature anomaly relative to the baseline for every year in each of the decades within this time series. I've specified that the regression, right? So the regression is here. I specified that the regression should apply only to the period 1940 to 2020. And I want that because this last decade has only 5 years. But all 5 of those years, we can easily see, are larger than the value that we would get by simply extrapolating the regression fit for the previous decades. Right? The trend is significant, but from Seaborn, we can't actually see how large it is. There are different modules that you can use. These I've included links as well, because these are modules that you might use for pre-processing or dealing with data for machine learning, deep learning applications, especially scikit-learn. Right? So This one's relatively simple. This one's focused on regression or building certain types of sort of bespoke models, and this one is pretty good for offering a wide range of tools that have been developed for dealing with these sorts of applications, right? So if we want to know the actual slope, we can simply do the linear regression. Here we've done it by decade as opposed to by year. And so that gives us a value in degrees C per decade for that period. And it tells us that it's highly correlated. The p-value is very small, and so on. And this is by decade, and so it's relatively conservative to the significance of the trend. So unsurprisingly, it's highly significant and large, right? So again, if you want to move on, we can look at the next notebook as well. But I'll pause here for questions, and so you can play around with the different plots or try making different selections, see how it looks.
Hey, Jonathan, I've got a question for you. I'm David White. I'm kind of crashing this conference. I'm the machine learning professor here at AIM Senegal, but my research is in time series analysis. So I'm wondering if with these plots you talk about at the very end, can any of those also do things like fitting ARIMA models or making cool graphics showing forecasting forward in time? I'm more used to R than Python.
Yeah, so I think we did. I had a student who was interested in that a while back, and we did put together an example for the class. So it is possible. It's not something that I'm especially familiar with. That was 5 years ago, I think. So Maria might know more.
She's not here right now, but I can ask her tomorrow.
Okay.
And if
Yeah.
not, I could also email you later when things are less crazy and hectic with the conference. But I would certainly be interested in more about how kind of classical time series analysis models get used in these contexts.
Yeah, so what I would say, I think all of that can be done in scikit-learn, right? So where I lost my link.
It was at the bottom.
In scikit-learn. And Xarray does play pretty nicely with those other modules, scikit-learn and stats models. So I've used some of the simpler methods from scikit-learn directly with Xarray. And I would say that you could do lots of other things as well, well beyond what I've needed to do.
Yeah, and if I can just ask one last question, is it also
Sure.
possible to do like spatiotemporal forecasting? So where we would take like the pictures you had before, the shaded heat maps of the world, but then, kind of see how they're changing over time and also where things are heading? I mean, I think there are like Bayesian algorithms for spatiotemporal forecasting. I just don't know if you can visualize it nicely with these tools.
Yeah, I would imagine so. I mean, again, it's not something that I've actually done. And so I need to think about how to do the visualization effectively. We have constructed some ways of dealing with three-dimensional plots. And so you could imagine something that would just show this kind of slicing over time and how it's evolving. You can do, I mean, animations are very easy using Xarray as well. There is a module that's specifically designed for producing animations easily from plots that are made using Xarray objects. I don't know if that exactly answers your question, but yes, I'm sure that there is this functionality somewhere. I just don't know exactly where.
Okay, awesome. Thank you. I'll stop taking up all the questions and see if anybody else has any.
more feedback for, okay.
Okay, thank you. If you can go back to the image of change in annual means ozone and CO over Dakar. Yeah. Yeah. Can we generally say that when CO increase, ozone decrease, or it is special the case of Dakar? That's my question.
Yeah, I mean, I suspect that there would be a correlation here. I would be reluctant to draw that conclusion from this time series alone. We can easily do that, right? So we have our 2 time series here, and I can show you. You can also do correlations directly with X-array. So if we want to do that, we would just do xr.core. Sorry, again, my keyboard switched computers. This will just give us a Pearson correlation, right? So it's pretty weak, and it's also not negative. So I think that probably what we see mainly here is there's this trend over the later period, but then there's this sort of dip in the middle, and it's kind of hard to tell whether that would be what that would exactly be related to. Right? So it's mostly just meant as an illustration for what you could do. And I wouldn't use CAMs for this analysis, I would say, right? Because it's sort of designed for larger scale features. It's also total column, and so there could be, especially for the ozone, a substantial component of the variability could be at higher altitudes.
Yeah, I mean, it definitely looks like there's correlation up to 2015 or so, or anti-correlation or something. It's interesting. We have more feedback for Jonathan. Look, is the question online?
Yeah, so it's a question about code for downloading data, which I haven't included here. Again, there are these options like X-array can work pretty seamlessly with threads, for example, OpenDAP. If you have if that's an easier way to deal with the larger data files. So X-array also works really nicely with Dask, which allows you to chunk the files so that if you have a very large file, but you want that's online and it's accessible in this way, but you only want a little bit of it, you probably can organize things so that you write all of your code and then you compute it, right? And so it will just pull the parts of the file that it needs to complete. But I haven't included any examples like that here. You can find these online for sure. So I think that's not the right way to do that. Here, I think. Yeah. All right, so I would close with the first half of the fourth notebook, which continues with what we just saw for time series. But while that loads, if you have any further questions about the time series or various things that were done in that notebook. All right. So in this case, I've constructed a notebook to work with sea surface temperature. And to reduce the size of the file, I've selected only the Atlantic between plus minus 40 degrees. This is the Kobe sea surface temperature. It's produced by JMA. It's used in the JRA2Q reanalysis and in various other applications. Right? So again, we can plot a simple distribution of the climatological mean for all months, and verify that it looks like what we expect. Yes, this is defined over the ocean. It is warmer in the tropics and in the Gulf of Mexico, and we can see these cooler regions where the upwelling can be relatively strong. Now, when we want to do area means, right? So in the previous example, we selected a single point, and we constructed our time series from a single point. But if we want to do area means, then we need to take into account the fact that where we're dealing with gridded data, and those gridded data, each grid cell doesn't have the same area. The grid cell area, in this case, it's a regular latitude longitude grid, and so it depends on latitude. And so in this case, we can define the weights for our averaging by the cosine of the latitude. And then to do the weighted average, we create a weighted object with those weights and then take the average, take the mean, just like we would. So we can do it without the weights as well, and we'll get a slightly different answer. It will be very similar in its variability, but it's not quite correct. So we're selecting a region in the tropical North Atlantic. It's consistent with the TNA index. So 55 west to 15 west and 5 north to 25 north. Here you can see that the order in which you index a variable, if you're using the selection, it matters, right? So in this case, the latitude for the Kobe sea surface temperatures is ordered from the north to the south. A lot of ECMWF products are initially organized in this way as well. And so we have to select from the north to the south, where in other cases, we would need to select from the south to the north. And so if you go through and you're selecting a particular area and you find that your array is empty, then probably that's the reason. Right? You just need to double check your coordinates, see what order they're in, and then rearrange how you are selecting the data from that object. Right? So here we apply that weighted average. Now we have the sea surface temperature in the tropical North Atlantic. Right? There's lots of other information about indexing. You can see all of that here. But I'll leave that as an exercise for you to go through at your convenience. All right, so let's say we want to calculate an anomaly relative to the pre-industrial climatology. We can define that as 1850 to 1899. We don't want the annual mean here. We want to actually see the monthly variability, but we want to subtract a mean annual cycle for some baseline period. And so we set the baseline period, 1850, 1899. We group by month, and we take the average. Right? So this gives us a mean annual cycle covering this period here. We take our full time series. We also group by month, and we subtract that, and we get the same as we had before. We have anomalies from the mean annual cycle. So X-array also makes rolling computations very easy, and there's a lot of flexibility here as well. You can define a lot of different windows. In this case, we use a standard boxcar average. We have a rolling window of 60 months, so 5 years. And we want the value to be centered on the averaging window. And then we drop the parts of the time series at the beginning and the end where we don't have 60 months to average, right? We could also add this keyword here. So let's say that we just want to taper it towards the edges of the window, but we want to have a value for every month, and we can do that by simply adding the minimum periods. But in this case, we just eliminate the periods for which we don't have 60 months. We can do the same thing as we did before, so defining a decade dimension, which is attached to time in this case, as opposed to year, because we've kept the monthly mean information. And then again, we can make a plot using strip plot and a line plot and having a couple of different lines on the plot, right? So we have the anomalies for the individual years relative to the pre-industrial climatology. They're now colored, they're normed by the magnitude of the anomaly. And we have also a 60 month rolling mean time series and a 12 month rolling mean time series as the thin line here. And so again, we can see the warming signal in the sea surface temperature over time, right? And so there's lots of different ways that you can chop your data, that you can plot it to visualize, you know, what story you want to tell. One of the problems that comes up when you are plotting time series using X-array, a lot of times it's helpful to make sure if you are plotting data from more than one data set, a lot of times it's helpful to make sure to require that those have the same time axis. So you don't want something where your monthly means are defined on the 15th of the month in one data set and on the 1st of the month in another data set, because then when you take the difference, it's going to give you no values because it thinks that they are at different times. And so to do that, you can simply replace the time axis. I'll give you an example for that in any other exercises that I'll attach and put in the GitHub later on. Right. There's more information about that and the various problems that you can run into here, but there's a lot of ways to deal with them. And I think they're less of a problem than they used to be. A lot of times for climate indices, we want to remove a trend. And so again, X-array makes that quite easy. If we don't care about all the additional information in the trends, we can simply do a polynomial fit. Here we have the first order, the second order polynomial, the fourth order polynomial. But why do we think about that? Well, a linear fit is maybe not the best option in this case when we have such a long time series and it's pretty flat in the beginning. So we might want a higher order polynomial for the regression for the trend. So what does that look like? Here, I'll show you the polynomial fits for those three examples. Right. And so in this case, we have the linear fit. That's the yellow line here. You can see there's too much warming near the beginning and too little towards the end. The quadratic fit, I would say, provides the best option in this case because it is a little bit less sensitive to the endpoints. The fact that we have a relatively warm year at the very beginning of the record, and we have a very warm year at the end. So that's 2024, we remember, right? The North Atlantic was extremely warm in that year. The record was almost a half a degree warmer than any other before. Right? And then for the rest of this notebook, I'm not going to go through this one in detail. Maybe I'll just go ahead and run it so you can see what the outputs look like. But for the rest of this, I'll show you another way of removing nonlinear trends. Basically, the idea here is that you want to take information in time, lots of information in time, and sort of evaluate the lagged relationship. And so by defining a large enough lag, you can isolate the low frequency and variability in long-term trends to then pull out the higher frequency variability from that record. Right? So again, now we're taking the spatial pattern. The main advantage of this approach is that we get a spatial pattern for the trend as well. And then we apply this extended empirical orthogonal function analysis to a reduced data set like Maria mentioned in the morning. Right? So glossing over all the details and just showing you what it looks like, how it compares to the others, right? And so this is the trends, the low frequency variability that we get out. And so you could say, okay, well, this is a very active volcanic period. Here's another one. And so it makes sense that the global trend would have dips in those years. But this could also be multi-decadal variability. There's still active debate, which I'm sure many of you are aware of, as to whether the Atlantic multi-decadal variability, what part of that is internal and what part of it is external. How much is it regulated by periodic changes in the number of large tropical volcanic eruptions, and how much is it regulated by processes within the Atlantic Ocean, right? And so it's possible that this wouldn't be the best option because we might not want to remove the multi-decadal variability. But in other cases, if we want to really look at the interannual variability, then this might be something that we do want to take away. And we can't do that with the polynomial fits that we have here. Right? And so after that, you can then kind of continue the analysis and say, all right, so I want to see after I take away that low frequency variability, what do I have left? And in this case, if we plot this, we'll see something that looks kind of like the Atlantic Nino, but with a much broader pattern in the latitudinal direction. And then the second mode is a TNA mode corresponding to what we looked at above. And so you can see tropical North Atlantic, tropical South Atlantic, this dipole pattern, which shows up. And then there are various other things that you can do. You can take a look at the rest of the notebook. If you have questions, you're very welcome to get in touch. Send me an email. The fifth notebook then builds on what we have here with this EOF analysis and does some shows some other things that we can do with that. And what I'll do is I'll finish off these exercises that I put together for the monsoon onset, and I'll add those to the GitHub probably tomorrow. And then you can also go through those when it's convenient. All right, so we've got 5 minutes left, I think, if there are any questions at the moment. And I'll also mention that in that last notebook, I took some time to point out where there are options, so where you can make changes and play around with the settings. Right, so here you got an option, like so, right? These are just some demonstrations of the various types of things that you can do. There are, of course, lots and lots more. I do have some other notebooks that I put together for some courses. And so if you want more examples, you can get in touch.
Right. Any questions or feedbacks to Jonathan? Jonathan, I don't see any hands up here, so it seems okay. Next question.
It's a lot of information. And so I think take your time. And so basically, the tools in these notebooks can be helpful for setting up the data and to get a sense of what patterns or relationships might be in your data before you start applying machine learning, neural network types of models, right?
Jonathan?
And so, yep.
Can you just go back a little bit about the mode with embedding? So I don't understand.
This one, yeah, right.
Very
So, yeah, and I think it's kind of a neat approach because it allows us to deal with this nonlinear low frequency variability. The idea here is the embedding is 120, and we have a monthly time series. And so that means that we're basically looking at patterns that are evolving on timescales of 10 years or more, right? And so we're trying to maximize the variance in the patterns that we see on those timescales. So if we use the global sea surface temperature, it's even a little bit stronger because then we could eliminate some of the dependence. This is the Atlantic that we're looking at, right? But that's the basic idea. These parameters, you can look, I believe it should be linked here, right? So there's an example. I follow the example pretty closely, but there are other examples also using EAOFs or MSSA on the website, the tutorials that they put together for XEOFs. I think it's a really nice package and it shows the advantages of the foundations that are now provided by Xarray. So 10 years ago when I mean, more than 10 years ago when I started in this job, none of this was available. And so we were basically doing everything from scratch. And it was a lot more difficult. Right? And so I think that the fact that we have these really nice tools that are built on this ecosystem is major benefit. And yeah, hopefully, as you get further into it, you can also think about ways that you can contribute to expanding that. Right? So if the tools that you need are not there, everything is open source. You can kind of look at how you could construct it, or how you could adapt tools from other arenas to this ecosystem.
Okay, Jonathan, thank you very much. We have to thank you very much at this point.
Yeah. It's 40 past.
Yeah. So have a good evening over there. And here we are going
Right.
for
Thank you.
break.
Yeah.
Yeah.
All right. Yeah. Have a good break, and see you tomorrow.
Yeah, Jonathan, have a nice evening. Thank you for your time. So we are going to have a coffee break, and then we come back for the downscaling using deep learning with Redwan. Redwan, are you online?
Yes. Yes,
Okay.
looking forward to. Have a nice break.
Go grab a coffee. Okay, so online people will come back around in half an hour.
C'est lui ton boss? Hein? Taylor. Oh, Patrick Low. Ah. Séeréer gi kii mun na la diriger kii ah kii kàccoor bi yow amoo boss de Alex time is up.
Okay, welcome back, everyone. So I think this is the last hands-on session for today, and it will be led by Red One. And you can take over and share your screen, Red One.
Yeah, thanks a lot. Thanks a lot, and welcome back. So yeah, I will take some time to share my screen, and in the meanwhile, I've sent the link for the GitHub notebook. It's on the chat. Okay, so first, can you hear me well? There's no issue. Okay.
No.
Okay, great.
Yeah, we hear you well.
Great, and you see also my screen, right?
Yes, we see it also.
Amazing.
Yeah.
Okay.
Wait, just do it slowly, that everyone is on the same page, right?
Yeah, sure,
Okay.
Sure. So we'll go really very slow for this tutorial. I will take really time to explain everything. I know that there are a lot of participants that are maybe not very familiar with deep learning, and so I'll try to make things simple for everyone. So please do not hesitate to stop me wherever you want, whenever you want to ask questions. Just please do not hesitate. But before that, I would ask every one of you actually to start right now and open the Colab notebook. So Jonathan explained Colab, Maria also. So yeah, I don't need to explain it again. So just go to the GitHub page that I've shared in the Zoom chat, or that you can also have access from the document in the drive, and you can easily just go here and click on this button. When you click on this button, it will just open the notebook directly in Colab. Okay, so please, if you can, all of you do this with me at the same time, and you will get a page like this. All right, you will have your notebook open on Colab directly. So just to be sure everyone is with me on the same page, we will do some very quick steps together, and then I will explain to you the tutorial. But I just want to gain time because you will need to download the data and it can take some time. So I would love to do this with you and finish with it, leave it to download the data, and then I will start explaining the notebook. So when you get to this page,
Wait.
yeah. Yeah, please let me know because yeah, it's a little bit difficult when you don't see everyone. So just let me know when everyone in the room has access now to this page, to the Colab notebook.
What? No. You click the authorization, and then you go OK. Go to OK. So you should have the then this one. Yeah.
Yeah.
Panicking. It's okay. Everyone is the same page. Yeah, we can move on.
Great, let's go. So the second thing I would love you to do is to click here. So I have my page here in French. So if you are using an English like Google Chrome or something, you will see something like execution or something very similar. And then you will go here and you modify the type of execution. Okay, so you see here in French, it's modifier le type d'exécution. All right. This tab, modifier le type d'exécution, or you will find it in English easily. It's not very complicated. And then you'll see this little window. And here you can choose to run the notebook on GPU. This will be very important for our notebook to get today, because if we run it on the CPU, which is here processor, it will take a lot of time to train the neural network. So it is very important to use GPU here. So you just click GPU and then you save, okay? So maybe some of you will ask why GPU, etc. I will answer the question later. I just again want you to like do these first steps with me, and then I will go to each part like slowly and explain everything. But just do this with me right now so we save time. So after that, you connect. You see here there is this button connect, or probably you will be connected automatically when you choose. And when you see this green check, it means you are now connected to a GPU card in a virtual machine of Google somewhere in the world. Okay. So these details maybe doesn't matter, but now you have access to a GPU, and this is what is interesting for me. You see here, you have now access to a GPU, and it is free. Google is giving a free GPU. It's not the best or the fastest GPU in the world. It's a normal, good GPU to do like some exploratory work, but it is free. So why not use it? So yeah, let's go. Let's use it. Then when you have access to the GPU, so I think probably all of you have access to the GPU, connected to the GPU. Sometimes in some tutorials, I see, for example, 1 or 2 students, they didn't get access to it. It's very rare, very rare. So probably you have all of you have access to GPU. Okay, can you please check, Mohamedou, if everyone has access to a GPU from Colab? If you see here GPU.
Oh wait, some of them has issues to access to the. That's what I'm asking.
Again, to remind you, it's here. Execution, modify type of execution, and then you select GPU, and
Red
then
one.
you do save. Yeah, yeah. Let me know. Yeah.
Wait, couple of them still did not have access to the GitHub. Go there to the Google Colab yet. Okay.
Yeah, it's just
wait,
yeah,
just okay.
Yeah, I'm just showing the GitHub page.
Go here. No, some of them were not connected to the their Google email. That's why.
Okay, okay.
Quand je demandais ça, tu étais où? Tu fais pareil. Tu fais pareil. Are you there?
Yeah, if you have used Colab for the previous session with Jonathan, it should be fine.
Tu étais déjà connecté à Google Colab? Ça commence à fonctionner là. On devrait voir. Il devrait apparaître ici.
I'll just probably ask for the others so we save time to just run the first, second,
Quand vous exécutez après l'examen.
third, and fourth until here, until data loading. You run also data loading and just let it wait for the others who have already access to Colab. Just run the first 4 cells, okay?
Hey,
Because this one will
Redouane,
take some time.
can I cut in for a second?
Yeah, sure.
So I'm the professor in the machine learning. So
yeah, nice to meet you.
You know, the internet here is a little bit slower probably than what's running. So for example, when I started running that cell that you just pointed to about 5 minutes ago, and it says it's going to take 9 more minutes. So for us, it'll take us much longer to run that cell than it will for you. I think for most students, they can expect to have the data in about 15 minutes.
Okay. It's okay, it's okay. I just wanted to run that, and then I'll go and present what is that statistical downscaling, explain a little bit what we will be doing, but I just wanted to save time. But yeah, it's completely okay. I mean, even for me, you see here, the expected time is like 30 minutes. It's so random. It's very random.
Ça viendra ici, si vous êtes en GPU ou pas. Redouane.
Yeah.
Can you just click, because this is the, this is where, just click on the upper right, just to show the GPUs and so on.
Yeah,
because
it's here.
if they are able to run it, at least where they're supposed to see it. Okay.
Yeah, they're supposed to see this here, GPU here.
Click the arrow.
When you click here.
Yeah, this is what you have normally. If it runs properly. Have you already access to the Google Colab? Have you already access to it or not yet? Yes or no? Okay, wait. Non, en principe, est-ce que vous êtes connecté? Est-ce que vous avez le lien là où est-ce que se trouve?
Oui, j'ai voulu passer par le GitHub et puis.
C'est bon?
C'est bon, ça marche, mais ce qu'il dit, quoi, on ne connaît pas c'est lequel des liens.
Non, c'est pas ici. C'est un autre fichier.
Oui.
C'est celui-là, statistique.
Oui, il faut aller là-bas. Après, copier sur le lien, copie le lien. Où vous le copiez si on va dans le browser.
If you're on the GitHub page, just click here. Click on this button here and you'll have your Colab.
C'est ton ordi, en fait. Ça doit être... c'est à cause de la machine. Mais attendez, peut-être ça va marcher. Vous n'êtes pas capable de... OK. Yeah, everybody. It's okay. It's okay. It's okay. Just wait. Just wait. Just wait. Just wait. Okay, go ahead. Yeah, you are reading Google Colab. Yeah. Okay. Okay. So, okay, yeah. C'est bon, c'est mon problème. Oh. Attendez que ça charge. Ok, allez là-bas. Non, je pense que peut-être son ordi là. Comme ça se connecte avec le Google là. Allez-y. Non, non, pour lui, c'est trop lent en fait. Ça n'arrive même pas à faire. Attendez un peu. Ok, cliquez. Non, ne touchez pas là-bas. Cliquez ici. Ça va demander. Ok, c'est bon. Vous pouvez suivre ici en attendant. Is everyone on the same page? So you can carry on, Redwan.
Okay.
Yeah.
So if you got access to the GPU card, you can actually run the first cells, right? You run the first one. The first one is just like to install some of the libraries we will need for this work. But what is good with Colab is that you have already, for example, PyTorch, which is the deep learning library we will use for this tutorial. It is already installed. So here I just added CartoPy. I remember Jonathan also talked about CartoPy. It's a good library to like visualize maps, etc. And then what you would do is you probably will see a warning like an error. Don't worry about that. You just click cancel. It will not change everything for you. So it's okay. I mean, even if you see a little warning, it's not a problem. Okay. Then here we import the libraries we will need. Here you can check actually the GPU card you have access to, because when you use this NVIDIA SMI command here, you can check, for example, that you have access to this Tesla T4. Tesla T4 is a kind of a GPU card, all right? And yeah, let me just tell you about this part, and then I'll go and explain maybe what is a GPU, because I talked a lot about GPUs, but maybe some of you don't know about it. So here, this is the most important, I think, cell that you need to run right now, because it takes a lot of time and it's actually very random. For example, it took me like 2 days ago, it took me 3 minutes to download all the data. But now when I tried, it takes me like 25 minutes. So it's very random, and probably it's maybe related to the fact that we are all on the group trying to access the same file. Maybe that's the reason. That's why it takes a lot of time. But please just run the cell, leave it download the data, and we can start together and can explain to you what we are be doing in this tutorial and give you some ideas. But please just make sure that everyone is on the same page with me. Everyone is starting to download, and then I can continue.
Is everyone on the same page now? Okay. Well, you can plug in there. Okay, up to now. Yes, supposed to do exercise. Not. So you can carry on then.
Okay.
I think maybe the downloading of some. Yeah, it can take some time because there are many people here. I don't know what is how.
8 minutes.
8 minutes, yeah. But if you have finished, you can just continue.
Yes. If you finish, just continue running the notebook,
no,
and you can follow.
You. If you finish to download, you can just continue step by step.
Okay.
Tomorrow
Let's go.
you are going to give the presentation.
Yes.
So maybe
yes.
you can manage just
All right.
as we're starting at 9:30, maybe we can just, for the people this evening, you have just to carry on the exercise on your own.
Yeah. Okay. I understand. Yeah.
It's better at the hotel.
Okay.
No?
It's the end of the day right there, huh?
Sorry then.
Yeah. Sure. So okay. Let me just continue.
Yeah,
like
if you arrive a bit early, you can.
Yeah. Let's do like that. Okay. So I'll go back slowly and talk to you about this notebook. Yes.
It's down. Right. Just and then we will get back to this while it is downloading. Okay. Go ahead.
Okay. So, yeah, let me talk to you directly about the GPU. So GPU cards are, so if you see my screen, so let me show you. Yeah, for example, yeah, these are GPU cards. So they were very known for example, people who play video games. They need these cards in their laptops to be able to run very advanced, let's say, video games, because it does a lot of well, algebra, let's say algebra, inversion of matrices, etc., that are very quickly in compared to CPU. CPU is the classic processors you have in your laptops. Okay, so GPU cards are interested for video games to do visualization. Are interested also for people who are doing, for example, cryptography. If you remember mining cryptocurrencies, people needed a lot of GPUs. But we found also that it is very important for deep learning research. When you do deep learning, actually you train neural nets. So neural networks are these very famous now machine learning method, and they need GPUs to be able to train quickly, okay, compared to CPUs. To give you an idea, sometimes, so I will be very generalistic here, it's not very precise, but sometimes it can be like 10 times slower to train a deep learning network on a CPU in comparison to train it on a GPU. That's why I'm telling you that having a GPU is very important to be able to train deep learning methods very quickly. All right. So let me go back to our problem here. So in this problem, we will talk. I would like to show you a simple example of doing statistical downscaling with deep learning. Okay, there is two things I need to clarify first: statistical downscaling and deep learning with units. So I found this morning a very nice picture that probably will give you an idea of what is statistical downscaling. But this is coming from general imaging. So this is Nano Banana, which is a model from Google that does image editing. And it is very interesting because here, for example, you can use a picture that has a very bad resolution, and you can, with the model, make it finer, make the resolution finer, make the resolution higher. Okay, so you upscale it. This is the term used in classic image processing. We use the term upscale. Okay, so you see the idea here is to take an image which has a bad resolution and you want a higher resolution image. All right, so this is what we call upscaling or super resolution when you do classic image resolution, image processing. But in the context of climate modeling, I'll show you. So these are from the slides from tomorrow, but I can show you now. In the context of climate modeling, what we want to do is we want to go from a model that has a coarse resolution, like for example, climate models which have 100 kilometer, 150 kilometer grid size, and you want to reach a finer grid resolution with, let's say, maybe 10 kilometers, maybe 5 kilometers. So it's a little bit the same thing, but in classic images, you don't have physics, but here we do have physics, right? So for example, you want a field, a temperature field or a precipitation field, which was coming from a coarse resolution product, and you want to go to the level of a city or to the level of a country. Okay, so this is what we will try to do in this notebook here. We want to take fields, precipitation fields, and I chose precipitation because it's a very challenging variable. We want to take coarse precipitation fields and try to upscale them or downscale. When you are in climate modeling, we talk about downscaling. So I will be using the term downscaling from now on. So we want actually to downscale that map to reach a higher resolution. So if you want to have an idea, well, it's in the end of the notebook. You see here how we go from an input which is coarse. So this is precipitation data. And we want to reach a fine final resolution equivalent of this input here. You see, for example, the second example is more clear. You see here how the resolution is coarse. We don't have a lot of details. And here we have more details on our precipitation map. So that's the goal today, to move from a coarse to a fine resolution map of precipitation. But how can we do this? Tomorrow you will see a lot of methods when I'll do the general presentation. But in this tutorial, I chose to show you one method which is very popular now, and it is based on units. So what is units? I don't know if people are familiar with units. Can you please, Muhammadu, ask in the room who maybe knows units? How many people know units?
Can you raise your hands? 2 people.
Okay. Yeah, I was expecting this. No worries.
Oh, yeah, 4,
All
5,
right.
6.
All right. All right.
Yeah, you have maybe one fourth.
Okay, it's okay. It's okay. I understand that this could be a little bit difficult for people who have never done deep learning. This would be difficult, but for people who know, for example, what is a convolutional neural net, I can explain what is a unit. So let's start like simple, okay? For people who doesn't know what is a convolutional neural net, okay? So these are a type of architecture, what we call architecture of neural networks. You remember neural networks are this algorithm that is now the state of the art in many engineering and science applications right now. And convolutional neural networks are a version which is more adapted to images or maps. Because here, in general, with climate data, if you want to do some imaging application, well, you deal with images, with maps. So you need a convolutional neural net. You can, for example, of course, use graph neural nets. I think Maria will talk about this later. But here, a classical way to deal with images with deep learning is to use convolutional neural net. So a unit is an example, or it's a subcategory, or it's maybe a flavor of convolutional neural net. I've found in the internet a very nice visualization. I will look for, yeah, this one. This one is very nice. So what you do in a unit architecture, you have images in input and an image in output, okay? So originally, units were developed to do semantic segmentation. So for example, finding classes in image. You have, for example, an image with 3 people, etc., and you want to find these classes here. This is what unit was originally developed for. What you do in a unit is that you take your image, you do a lot of processing with convolutional layers. So you do a lot of convolutions. You of course train specific convolutions for your neural net, and you have a specific encoder decoder architecture. What you mean by that? If you know, for example, EUFs or PCA, you do some dimensionality reduction, right? When you use EUFs. So you do dimensionality reduction and then you go back. You go back to your original space. So it's a little bit like that, okay? So what we do is that we encode the information until this bottleneck, and then we decode the information. So again, it's a similar idea, okay? It's a nonlinear dimensionality reduction, if I may. So what you do is that you use a convolutional neural net specifically with this encoder decoder path, but the unit is very the innovation, let's say, of unit is on these skip connections, okay? Because here you see the information flowing from the decoder until the bottleneck, then it goes back with the decoder, right? Encoder, decoder. But the innovation of the unit is that the authors, they said, when you do compression of the data, you lose a lot of the high frequency, okay? Again, like with EUFs, when you do EUFs on your data, if you have a high resolution data and you do EUFs and you go back, you see sometimes that you lose, especially if you select a number of coefficient, you lose some information when you do the encoding, decoding. So it's the same. It's the same with with the convolutional neural nets encoder decoders. So they said we will add some skip connections that will keep some of the high frequency information so that we can have at the end a mix of information. The first part is coming from the decoder and the second part is coming from the skip connections. All right. So it's a very nice architecture, used a lot, very classic. Now it's traditional. If you have already got courses on deep learning, you already know what is a unit. If you've never done deep learning, the day you will start learning about deep learning, especially with images, I am sure you will have a course on units because now they are really everywhere. Okay. So first, do you have any questions about this part? I know it would be probably difficult for people who have never done deep learning, but if you have any question, even a naive question, do not hesitate to ask. So, are there any questions, or I can?
Wait. There is a couple of questions here.
Okay. Okay.
Can you just share the link of the unit by
This
adding
visualization, yeah, sure.
in the README file?
Yeah. Okay, I can do that. Okay.
Someone else?
All right, I will do that later.
Okay, you have another one. Yeah.
Yeah, thank you. I was asking about the choice for UNet. Why what motivated the choice of UNet? Why not just the encoder the encoder block, or why not another architecture like deep lab?
Yeah, that's a good question. Actually, it just depends on, you know, in the literature you will find a lot of architectures. All right, you will find probably maybe a simple convolutional neural net. You can find a combination of a simple convolutional neural net and a multi-layer perceptron. You can find also units. So you will find a lot of choices in the literature. The reason why here I used a unit, because of the idea I told you here about keeping the high frequency details. So I want to keep at as much details as possible. Okay, because suppose we use an encoder decoder and we just remove the skip connections. The very nice thing with this tutorial is that you can try this. You can change here. You can go into the architecture and just change the parts where I concatenate. So this is torch concatenate actually. So this is the skip connection. You can remove the skip connections and you will see how it affects the performance. And I know with units, if you remove the skip connection, you will find a little blurry image at the end. Okay, because you will lose a lot of the high frequency details. So that's the reason. So I'm not saying unit is the only solution. Of course, maybe there are others, but it's one of the solutions that I like very much. It's easier to train. It's easier also to explain actually, because some of the architecture are maybe over complex, and it also doesn't have a lot of parameters. That's also something I forgot to say, but it doesn't have a lot of parameters to train. I don't know if you know specifically about multi-layer perceptrons, but you can try, for example, to just take your image, do some sort of encoding part, and do a multi-layer perceptron at the end. But this will probably generate a lot of parameters, and you will have to deal with the optimization issues. So I haven't tried this myself, but again, this is a choice. You can try. And that's the goal actually of this tutorial. You can also play with it. It's not important to stay with unit. This is just an example.
So you have another one here.
So good afternoon, Redwan. So
yeah,
thank you
for
the presentation. So I've tried to do the same thing using my CPU. So
Okay.
I've downloaded the files.
Okay.
And I've used it in my own laptop. But the result that I've got is different to the result that you've got. For example, first for the value loss, you have got higher values than me. For example, can you come back to, yes.
Last function.
The last the images.
The last function.
The image.
Okay.
Here.
Yeah. So for you, it reached still 0.285 or something. But for me, the highest value is around 0.0275. And the best score also.
Okay, it's not a lot.
Yeah.
Okay, which is good, which means that you didn't, because your goal is to have a low loss, a low error, so it's good.
Yeah.
So
Yeah.
just continue your question. Sorry, I interrupted you.
Yeah, go ahead.
And also the best scores also. I think there is some difference between mine and you too, but
okay, my answer is it's normal. You know why? Because deep learning is based on non-convex optimization, so it's you don't have always the same solution. If I love to have the same solution, me and you and everyone in the room, I would have fixed the random seeds, but I didn't do that. Okay. So the first solution is just fix the random seed and everything will be reproducible for me, for you, for everyone in the room. But I didn't do it because I wanted to see what happens when you change, when actually the training starts from a different place. Because what happens when you do training of neural nets is that you initialize your neural net, okay? What does it mean? It means the neural net has random weights at the beginning. Well, cleverly selected random weights, but it's different for me, for you, for another person. The goal is to reach a very good performance at the end, but the way it starts or the path the optimization takes, it doesn't matter a lot. The important thing is to have a good result at the end. So probably I started maybe very far from the solution, but I approached the solution at the end. You see what I mean?
Yeah, I think at the end is the same. It's just the kink there that is a little bit different. Yeah.
Yeah, there is some
Or the
stochasticity actually in
validation
the
loss function. Yes.
Yeah, and
But
this is very normal, very normal. There is no issue neither from my side, neither from your side. It's very normal.
yeah, the training loss function is quite the same. It's just the validation. There is this kink that makes the difference, but the range is quite the same what he obtained.
Yeah.
I checked that. You have another one here.
Yeah, sure.
Good evening, sir.
Good evening.
Related to the UNet architecture, there are some possibility to add some function like optimization to increase the level of efficiency. Like UNet, you have a convolutional neural network, but can I add something like some optimization method, like I don't know, XGBox, something like that?
Okay. Okay. This is a little bit complex to answer. So you want to, for example, mix random forests or XGBoost with the neural net. Well, to do the training, it's difficult. It's very difficult to combine both. Because when you want to train a neural net, you need actually, because it's gradient based, you need to calculate your gradient of the loss function. So it's, in general, the optimization is based on gradient descent. And if you want to do gradient descent, you need to differentiate the parameters, the loss with regard to all the parameters. If you add the XGBoost with the UNet, it becomes very, very complex. So I don't want to say it's impossible, but it's very, very complex, and probably you will not gain a lot. It's already, I mean, units are very efficient already. I don't know what you mean exactly, but by efficient, is it like very fast? Is it like very easy to train? But it's very rare to see combination of the both while training, I'm saying. So for training in general, you have an architecture fully based neural nets. So it's not just neural net and some random forest. This is very complex to optimize. So in general, just neural net. So convolutional layers, you can mix convolutional layers with, for example, MLPs, multi-layer perceptrons, because these are neural nets. So yes, you can combine both. But convolutional layers and random forests at the same architecture and training that's very, very complex. And probably maybe impossible to train.
Okay, so can I have some limitation of the UNet architecture?
Okay, in terms of limitation, in terms of what specifically? Just limitations in general?
Yes, in general. Yes.
Okay, in general, limitations of units, well, units are very successful, to be honest with you, are very successful in many applications in classic imaging. For example, doing super resolution, doing classification, doing semantic segmentation. If I think about a limitation, well, the limitation is probably sometimes the cost. If you have a lot of data and you want to do a big unit and train it, it's probably costly, but this is applies to every other deep learning architecture. And there are even architectures that are more costly than units. There is one, if I think, well, there is one limitation is the fact that you need to divide by 2, for example, the size of your feature maps each time. Let me go back to here. So when you go from a stage to another stage, okay, you do in general max pooling. Max pooling in general, usually we divide by 2 the size, the height, and the width of the image. So if your image has 64, after your first convolution, you will keep it 64 with a lot of feature maps. But when you do max pooling, you divide by 2. So you become here 32 by 32. And then you do again 16, 8, and 4 here, for example, okay? So this means that in general units, they love when when the size of your images are can be divided by a power of 2, okay? So, sorry?
No, go ahead.
Okay. So, that could be a limitation, but it's not a very hard limitation. I mean, you can always do some kind of interpolation to make your image, your image with the size you want. So it's a little bit weird to say this, but units are very successful, so I don't see a lot of limitations with them.
Redwan?
Yeah, sure.
Maybe, I mean, it is still downloading. Maybe you could just walk them through the different steps.
Yeah, to be quick. Okay. Okay, let's go. I will try to be more quick, I think, and show probably directly the results so people will try at home. Okay, so when you finish the downloading, you can actually load your dataset. What we will do here is that we will take the initial dataset. So let me show again this last image because it's very nice to see. We will take actually the original dataset, which is from iMerge reanalysis product. And actually, you will see that this dataset has a 10 kilometer resolution. What we will do is that first we will degrade or coarsen the resolution to make it bad, okay, to make it worse. So we will take this dataset and we will degrade the resolution to get to a version that has a coarse resolution. And then the goal is to inverse the problem, is to go from input, which is coarse, to the target, which is fine. All right. So this is the general idea of this tutorial. So this is what I do here, and this when I read the data set. So when I read the data set, I will here create the coarse data set. So instead of the 64 boxes I have at the beginning, I will move them to 16 by 16. Because each 4 pixels, I will just do the mean. For each 4 pixels, I will just replace it by 1 pixel with the mean, okay? So this degrades the resolution of the dataset. So as you see at the end, I have, this is the shape of my output now, okay? Because the output is high resolution, 64, and this is the shape of the input. And I do have a lot of examples here because I took like years from 2001 until 2024, but I took only the June, July, August, September, and October months because these are the months where Senegal, where you have rain in Senegal. So you can actually check some examples here. Okay, so this is the fine target and this is the coarse version. You see here you have more details, and here you have just big blocks, big pixels, all right? So these are big pixels, and here you have details, all right? So when you finish, and of course this cell here, you can run it several times to see other examples. And this is very nice to visualize the difference between the coarse and the fine data set. Then what you will do is prepare the data sets for the deep learning for the UNet architecture, right? For that, I did some pre-processing first. If you already worked with precipitation, you know that precipitation is a very complicated variable. Why? Because it has a lot of zeros. It's normally, you don't have rain everywhere, every time. So it have a lot of zeros, and it makes the distribution of the data very skewed, very skewed to the zeros. Okay, it's not Gaussian. The dataset distribution is not Gaussian at all. So there are some tricks that are done in the literature. For example, doing a log transformation. So you just take log 1 plus x, and you manage to smooth a little bit the shape of the distribution. So this is very classic. You will find it in the literature. A lot of people don't work directly with the raw precipitation data, but they work on the log transformed precipitation. Okay. And also we do have a lot of small values sometimes, and these small values can be like errors, can be very difficult to explain when you have like for a specific point, a specific date, you have a value of 0.0001 millimeter. This is not physical actually. So what we do in general is that we do some thresholding. For example, everything that is below 0.1 millimeter, actually it's millimeter per hour here. Yeah, I can change this. We just set it to 0, right? We just put it to 0 to say that every value that is under 0.1 is considered no rain. It's like there is no rain, okay? And then you do what is very classic for deep learning, like training. You split your data set into train, validation, and test, okay? So the training data set is the data set you will train your unit on. The validation data set is a subset you will keep to try to check the generalization capacity of your unit to see if it's really very good also for data it did not see, because the unit will see the training data it is trained on, but we want to test the generalization on unseen data sets. And the test data set, you keep it at the end, and this is the data set in general you use to check your results for maybe more challenging case, etc. So here I didn't do something very I did something very classic. I just took, for example, I think I wrote it here. Yeah, I took the 20, let's say 20 years for train, 2 years for validation, and the last 2 years for test. Okay. So yeah, this I can skip. So yeah, this is the total number of samples for training and samples for validation and test. Here I define the unit architecture. So again, this is based on PyTorch. I know that Maria talked about Keras. Also, these are different deep learning libraries, but they are all doing the same things. But I like PyTorch because with PyTorch, you can actually change a lot the architecture, play with it more. It's more research oriented. While Keras, it's very simple to use, but it's very rigid too. You cannot do a lot of things, a lot of new things with Keras. But Keras is very good also, especially for like pedagogical content. So what I do here is I define the convolutional blocks. So probably I will not spend a lot of time here because some of you probably are not very familiar with deep learning. So please, if you have questions, do not hesitate to ask. And people who are familiar with deep learning, you might know this already. You know already what is a batch norm. You know already what is a convolution layer. So please, if you have questions, please just stop me. And this part, I defined my unit, okay? And then I started my training loop. So in the training, what you define in general is the optimizer you use. Again, as I told one of your colleagues, it's based on a gradient descent. So if you got a course on optimization, you know what is gradient descent. So it's a flavor of gradient descent called ADAM-W here, which is used. And a scheduler which plays with the learning rate of your optimizer. And yeah, this is very important. The criterion or the loss function we will use for this problem is the L1 loss or the mean absolute error loss. So it's the same thing, L1 or mean absolute error. Some of you may think why we are using this. We could use MSE, mean square error, which is very classic. So mean square error works very well when your data is Gaussian, has a Gaussian distribution. But as I told you before, for precipitation is too complicated actually. So you can try. I mean, you have the notebook. You can replace this, and you can try and do MSE loss. But you will see that the results will not be very good. Will not be as good as with L1 loss. So L1 loss is more adapted to like it's more adapted to this problem here because it doesn't smooth a lot the results. So the MSE in general, it smooths the results, and L1 is more like sparse. So there are some justifications why we are using L1 loss here. And then you see, yeah, sure.
Can you just go back a little bit?
Yeah.
Not on VNet structure, but at least could explain what is the pooling, the convolution, or
Okay, but I will try to be very quick because it will take a lot of time if I okay, let me
the principle.
Yeah, convolutional layer. I might find a very nice. Yeah, this one could be good. No, this one could be good.
Yeah.
So with the convolutional layer, what you do in general is that you know your images are actually numbers, are pixels with values, right? So imagine you have your image here with your with the values of the for example RGB images, or let's focus on our precipitation example. So you have just an image with the precipitation rate for each pixel. What you do when you do a convolution is that you train what we call a filter, which is in general usually a 3x3 matrix. And then what you do a sort of a weighted mean, okay? A weighted mean, what does this mean? It means that actually what I do here in this mathematical operation is that I multiply this value here with the value here, plus this value with this value, plus this value with this value, and I do the sum at the end, and it gives me the value here. All right? So it's an operation, it's a mathematical operation. It helps to detect features in image. So if you are very curious, you can look for classical filters. So if you look, for example, filters in image processing. So these are, yeah, these, for example, are very classical filters. Let me show if I find that classical. Yeah, for example, this filter here, it will smooth the image, okay? It takes an image like this and it will smooth it, okay? There are many other filters. For example, this filter will, for example, sharpen the image or do the edge artifacts. This is a classic convolution. You need to, when you convolute a picture with this, either you make the resolution better, maybe you want to smooth the image, maybe you want to enhance the edges, etc., etc. So this is the goal of convolution. The goal of convolution is to extract some features from the image. But in the examples I'm showing you here, the filters are already fixed. So for example, this one is already fixed. It's 1/9, 1, 1, 1, 1, 1, etc. In the deep learning project, when you do convolutional neural net, the values of the filters are decided by the training. So it's the training part that decides the values of the picture. You don't fix them yourself. Okay, that's the difference. So yeah, this is what I can do if I can do like a crash course quickly on convolutional layers. So again, in convolutional layers, you learn filters, 3x3, for example, filters, using the optimization process. that can extract data sets, that can extract features from the image, from your image. So let me go back here. So here for the unit, we have many convolutional layers, a lot of convolutional layers. Because in general, in deep learning, this is why it's called deep. We don't use one convolution layer, we use a lot of convolutional layer, and that's why we call it deep learning, right? The second type of operation we use in general in an encoder-decoder architecture is called max pooling. Max pooling is very simple. In max pooling, what you do is that you reduce the size of the image or the size of your tensor by doing this simple operation. For example, in a max pooling, 2x2 max pooling, you take the 4 values and you take the maximum here. For example, in these 4 green values, the maximum is 100. So it's 100 here. Same for here, same for here, same for here. You have 4 values at the end. So if your input is 4x4, your output is 2x2 because you divided by 2 and the height and the width. Okay, so this is max pooling. So these are the two very classic operations that are used in a unit, right? Well, I hope it was clear because it's I know it's difficult to do this in a short time.
Yeah. I mean, you will get just opportunity to go back from that tomorrow. But it's good just to, in the exercise, you went very fast just to explain. You have to combine like the convolution and then the pooling and then so on, etc. It's kind of layers that are stacked one after the other one until, but carry on, please.
Okay. So, let me, so I just seize the opportunity to again show you this example here because now I got access to the data. You see, these are a lot of examples. You can run this cell many times. So this is probably a state actually where you have only zeros. If you see this, it means you have just zeros everywhere. So here, for example, let me do another, maybe last example, which, this example is nice. You see here the difference between the fine target and the coarse input. Okay, so let me go back. Just doing the definition of the unit architecture and the training loop. And then here you will start the training of your model. So when you start, so this is a basic PyTorch, so it's very PyTorch oriented. This code is very PyTorch oriented. So no worries if you feel that this is maybe not clear or something. So in general, and I added in the README a very nice introduction to PyTorch. But even if you did Keras or any other, or maybe TensorFlow, you will know that it's in general it's a similar thing. You start by defining a number of epochs. Epochs, what does it mean? Epochs mean how many times you want your neural net to scan all your data set. So you remember we have 77,000 images. So how many times we want our neuron to scan them all? So let's say, for example, 20, because I don't want to spend a lot of time. I just did 20, okay? So what you then define, which is important, so this I will not explain it because it will take a lot of time. So what you defined also is you try to monitor the validation loss and the training loss. So you need to check that your neural net is training well on the training data set, because this means that the loss, the error will decrease over time, will decrease over epochs. And you want also your validation actually loss to also decrease with the epochs. Because what happens is that if you leave your neural net train a lot, it will memorize the training samples. It will become so good on the training samples, but it will become bad on the validation. And of course, if it's bad on validation, it will be bad on test. And we don't want that. And this is what we call overfitting. Okay, so we don't want overfitting. We want actually our curves to be going together, going decreasing together. But if it starts to go up a lot, you need to stop your training. So this is what happens when you let it train. You will see that it saves the best neural net, and the best is decided by the validation. It's not decided by the train, because the loss with the training will always decrease. Okay, you will always see that the loss with training is decreasing, but we want actually to have a very low error on train and on validation. So please remember this. We want to be also good on the validation dataset, not only on the training dataset. So the training is very quick here actually, and this is thanks to the GPU cards. If you do the same on CPU, you will see that it takes a lot of time. So here we are already at 3 epochs. I think it will take probably 10 minutes to train, but then when you finish, you can look at the loss functions. Again, as I said to your colleague, it's okay to see some spikes, but the important is to have a trend. The trend needs to be decreasing. And of course, if I leave it for more, probably it will also decrease on the training, which is the blue curve here, but maybe at some moment, the validation loss will start to increase, to go up, which is a bad thing. So yeah, this is in general monitored. You can monitor this when you do your training because you save only the best validation loss. And then when you finish, you will go to your test dataset. So you see here, I'm using the test dataset. So the test dataset was never seen or used by the unit. So here is the moment of the truth, actually, because you want to see if your neural net can work even for different maps that were not used in the training. And you can actually generate here 3 examples. You will give it this input, for example. This is the target you are trying to get, and this is the result of your unit. So what do you remark here with me if you look at this? For example, look at this one. This one, I like this one here. You see that first, we have actually a better representation than in this, because here it's very blocky, it's not continuous, etc. Anyway. So here, at least it's high resolution, of course, because it has 64 by 64 pixels, but we still lose a lot of the high frequency detail, right? Are you agreeing with me here? So it's good, but it can be better. So this is one of the things I want to let you know also, is that this problem is a very difficult problem actually. And even if I'm telling you that this is the simple case, it's actually very difficult to solve this inverse problem. Why? Because imagine you have just this image here, your input. There are actually a lot of possibilities for a high resolution version of this. Forget about the truth. Imagine we don't have the truth, we don't know it. We only have this image here, the coarse image. So there are so many ways we can generate a high resolution version of this image here. And this makes the search space very large. So what happens is that a neural net, which is deterministic, okay, I will probably say this tomorrow, but a neural net which is deterministic will just try to like collapse all the possible solutions in one. And that's the reason you have this kind of blurry, a little bit image, okay? If you are very like curious and maybe want to work on this topic, you need to know that if you want to have high frequency details, there are a lot of techniques, but the state of the art currently is using, for example, well, the classical term is generative AI, but probabilistic methods. Probabilistic methods, you might hear of diffusion models, GANs, generative adversarial networks, etc. These are methods that can generate possible solutions. These are probabilistic methods. They don't give you only one answer, they give you many answers. And these are better, but I didn't, the reason why I didn't do them here in this notebook, because they are very costly. So they take a lot of time, a lot of time for training, a lot of parameters. They are also over complex for a very easy like tutorial for a summer school. So of course, if you are interested in this topic, if you want to work on this topic, please do not hesitate to contact me. So yeah, this is about this notebook. I really encourage you to do two things. First, of course, run the notebook end to end, from beginning to end. The second thing I would I would really recommend you is to play with these hyperparameters here. Try to change them. Maybe I used a very big neural net because here I have 7 million parameters, but maybe if you use 16 here, a smaller architecture, maybe it would work well too. I didn't check this, but I encourage you to do this. And the second thing I want you to check, yeah, actually this was the second thing. So the first thing, run the notebook from end to end. The second thing, try to play with these hyperparameters here and see the impact on your training and on the results. And yeah, I will add another thing. If you are like courageous, try to think about how can we deal with this problem, especially the problem of imbalance, because we have a lot of zeros in this data set. So this is a very difficult problem when you have a data set, when you have a lot of zeros. So this data set is probably 80% zeros and just 20% with values, with actual values. So how can you deal with this issue? And yeah, thanks a lot. And of course, I shared my email, and I'm still here for questions.
So thank you.
You're welcome.
Do you have any questions? So just do you plan to talk about variational encoder tomorrow or no?
Not really, because I want to focus on the statistical downscaling and also bias correction, because bias correction is very helpful to statistical downscaling. But you know, I already have other slides. I can add them, but I don't know if maybe there is. I don't know. Is there a lecturer that plans to do that later? Because if not, I already have some slides. I can show them tomorrow.
No, there is no lecture.
Okay, so yeah, I can take some time and explain what is an encoder tomorrow.
Yeah, there is one on the 2023, but not this time.
Okay, no worries. Yeah, I can tomorrow take time and explain what is an encoder decoder, what is a unit, and maybe also a little slide with convolution layers.
Yeah, thank you. I had two quick questions. First is about the model, the unit. So if I understand, we are using the architecture and not unit as a pre-trained model.
Yeah, exactly.
So
exactly.
you the architecture and train the model from scratch,
Yes.
right?
Yes. Exactly.
Okay. So my question is there any difference where using just architecture and train it from scratch and using a pre-trained model?
Okay.
The second question is about the optimizer. I saw Adam W. I know Adam, but not Adam W. So what?
Okay.
Why Adam W? Is because of the class imbalance or yeah?
Okay.
If you can.
Thanks. These are very, very nice questions. So the first question is why I'm not using a pre-trained model. So for the others in the room, a pre-trained model is a model that is already trained on another data set and that you can like just use and maybe fine tune or change a little bit for your data set. So the reason is first is that I don't know of a pre-trained unit for precipitation. So maybe it exists, but I've never heard about it. So that's the reason, actually. The second reason is that this is like a pedagogical reason. I want you to train this from scratch because it's a good exercise. But I don't know, maybe, but at the best of my knowledge, there is no pre-trained model on precipitation, and especially on Senegal. Maybe there exists for the North countries, but I'm not sure for the Global South. So that's your first question. Your second question, yes, I'm using Adam W. We'll show it to the others. Yeah, this optimizer here is Adam W. And actually the difference with Adam, so Adam is very classic. It's again based on gradient descent with some momentum. There's some nice ideas in Adam. So Adam W, they have this idea of adding also weight decay. So they want to do some kind of regularization they add some regularization that helps in optimizing, and they also do some kind of normalization of the weights when they do the optimization, and this helps actually. It's just a matter of helping the optimization. I'm not saying Adam will not work. I think even if you remove and you use just Adam, I'm sure it will work. But I just like Adam W because it's more stable. Let's say for my case, I found it more stable. But for these kind of questions, I think no one will give you an answer, a direct answer. What we do in general is that we try both, and we take the best. That's what we do. But I'm not sure someone will just tell you, yeah, Adam W is always better than Adam. I'm not sure about that. So yeah, you just try and you take the optimizer that works best for your case.
Okay, so do you have more questions? Okay, well, so if we don't have more questions, right one? Okay. You forgot. Okay. Yes.
Okay. My question is, could you also talk about the data augmentation?
Okay, so no data augmentation was done here in this notebook, but yeah, it can be done. So for data augmentation, the idea is that you want to have more samples for your training, and for the new samples you want to add, you can use the existing ones. And for example, you use the existing ones and you do some transformation. Like for example, you do some rotation, you do some, I don't know, some yeah, in general, rotation is very classic, or you do some cropping, etc. It was not done here because I think we have already a lot of data. We have here like 88,000 data, yeah, 88,000 samples. So I thought maybe it's not necessary in this case. But yeah, in some cases when you don't have a lot of data, yeah, data augmentation is very very helpful.
Okay, thanks for this this part. My question is about the past question of my colleague about the using of pre-trained model. I think it is the transfer learning. If I understand your answer, you say if I think it's not possible because we have not already a model for the I think the processing the in the presentation in the Senegal, so it is not possible. I don't understand very well because in my past understand we can take the model pre-trained in the another condition in the another thing, and we transfer for if I not have much data to perform my neural network.
Yeah, what I'm saying, actually, I agree with you, because what I'm saying is that, as you said, you need a pre-trained model trained on somewhere else. And as I said, actually, I don't know of other pre-trained model trained for somewhere else, you know, for precipitation. Maybe I didn't look, but in my end, at the best of my knowledge, I don't know of other pre-trained models, maybe trained on France, for example, that we can fine-tune, for example, for Senegal. Of course, this would be nice. But I don't know if there is someone like have already a pre-trained model for France on statistical downscaling on precipitation. And it's not always an easy task, because if we take, for example, the example I just mentioned, the precipitation in France is very different than precipitation in Senegal, especially in terms of seasons, etc. So if I were you, I would prefer to train from scratch. If I have the data and I know very well my data set, I would start first by training from scratch. And if I see that maybe the results are not satisfying, I would search for maybe a neural net trained for somewhere else that has probably the same climatic conditions, maybe in the same, I don't know, in the same latitude, maybe from South America, maybe from, I don't know, Southeast Asia, or somewhere that has maybe a closer climate to Senegal, and then I can fine tune it or do transfer learning for Senegal. So yes, it's possible, but I don't know. I don't know if there is a pre-trained model for that.
All right, so I think we can continue the discussions tomorrow when Redwan will give a talk and will also be on a panel. So let's thank him again.
Thank you all, and see you tomorrow.
Yes, so thank everyone that has spoken and thank the participants. I think we just close here and then come back tomorrow morning. Thank you.